بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Thank you very much for coming to lecture number 7 in our training program on mastering ChatGPT. And today, inshallah, we're going to talk about a very important aspect. We are going to discuss the core technology about ChatGPT and large language models, which is transformers. So transformers was proposed back 4 years ago and has made a complete revolution in the artificial intelligence research. And it was actually the key component that has enabled the release of what we know today as large language models, including ChatGPT or Llama models or the different other language models proposed. So by the end of the lecture, you're going to learn and understand the language model history and their applications. And also we are going to dissect the transformer architecture. We are going to explain the transformers component by component. And inshallah, by the end of the lecture, you will have a complete understanding about this technology and how it has contributed to the prosperity of language models. We're going also to construct language models from scratch. And so for the training, this is going to be the next lecture, because for the hands-on activities, we need to have a complete lecture to develop the language model from scratch and train it. So today we're going to focus more on the theoretical aspects about the different concepts, trying to understand the different mechanisms like self-attention, multi-head attention, and the different other components of a transformer. And in the next lecture, we are going to have a complete 5 hours lecture to develop in Python a large language model from scratch and also train it. So basically, this was the first transformer architecture that was proposed in 2018. So I guess most of you probably will not have any kind of understanding about what is this architecture, what are these different components, what is multi-head attention, but don't worry about this. So I promise you, by the end of the lecture, you will have a full understanding about this architecture. Okay, so this is what we are going to discover. This is the architecture of a transformer. It has different components starting from your raw input, that is the text, and then we're going to have input embedding. So if you have attended the previous lecture, you should know what is embedding, what is tokenization, which is the initial phase of data processing to prepare the data for being processed by a transformer architecture or a language model. And then, of course, we have different other components which constitute the backbone of a transformer architecture, and it has different type of learning parameters that will allow actually to develop language models. So please feel free to interrupt me if you have any question or if you want to have any additional information. Okay, so these are the different also equations that captures the relation of a transformer architecture, and you are going to understand them during this course. Okay, so let me start from the very beginning. Okay, a language model in a very abstract manner. So we have already talked about this in the previous lectures. So we can consider a large language model from a black box perspective as like an engine that will do text completion. So this is basically the main objective of pre-trained language model. So for example, if I give a sentence like this: every morning I go to. So we can have different type of completions. I can say I go to the school. Okay. And now if we look at, for example, if I try this on OpenAI Playground, so we can see the probability of the next word or the next token that should come afterwards. Okay. So now here, if I say every morning I go to, so this is a context. This is an initial context. And now the language model, all the role of the language model is to predict the next token. So it will say the next token could be, for example, the article the with 42%, or my with 11%, or a with 7%, or work with 5%. So it will provide you a pool of possible next token suggestions based on what? Based on the context that you provided here in advance. And of course, now, if you follow a greedy approach, you're going to say, okay, I'm going to select always the most probable. But this is not a good strategy because you are going to kill the creativity. Okay, so creativity, it will allow that we can choose some low probability, but they are likely to happen after given the following context. And of course, now, if I choose the word my, I will have a context. Every morning I go to my, and then I need to predict the next token. Okay, it can be to my class, or to my school, or to my work, or anything else. So at every iteration, you're going to choose one of the most probable words that could happen, okay, given the context or given the sentence that we provide as an input. So this is the role of the language model. And basically, the language model here is nothing but a transformer architecture. Of course, it can be other types of neural networks, but these type of neural networks are not efficient enough to provide high quality text generation. And this is why now transformer is the de facto standard for language model nowadays. Okay, so this is another possible completion also. Okay, another possible completion about what could be the next possible words. So every time we need to choose from a pool of possible next tokens. Okay, so I have talked about, if you see the probabilities that come afterwards, and I say it's not common that we every time choose the high probability token that can come afterwards. And this will actually affect what we call the randomness of generation, because language models are kind of random generators, but they're going to be completely random. They will try to generate a random text with a certain meaning. So during the inference of a language model, we can play with some parameters. And one of the most important parameters is the temperature. The temperature here, it can be a value between 0 and 2. And when the temperature is 0 or very close to 0, like in this case, we're going to have a low randomness. So what does it mean, a low randomness? We're going to choose only the high probability words. Like, for example, if I choose a very small temperature, I'm not going to choose words with low probability, like here, Paris. I'm going to choose the words, for example, from only limited number of words, V or downtown, or probably only this, or Washington at most. Okay, so I'm going to reduce the randomness. I'm not going to choose something that is unlikely to happen. But what is the advantage of this? So the advantage of this one is that it's going to provide a meaningful and a reasonable output in the text generation. However, it's not going to be creative, because creativity is related to randomness. When you have something more creative, it means it can explore a larger number of words in the generation. But imagine if we put only the extreme case, temperature equal to 0, is going always to choose the highest probability word. And in this case, it's going to be always the same completion, regardless of how many times you are going to make inference. So when we choose, in the other hand, if we choose a high temperature here, so you will have a completely high randomness. And in this case, it will be too creative, and this will lead to hallucinations. So let me just show you an example on OpenAI. Okay, just to grasp this context. I'm going here to go to text completions. And let me choose some of the models. Like, for example, this one. Okay, and you can write every, okay. And here I'm going to show the probabilities, the full spectrum of probabilities. Every day I go to, well, what is the here? Every morning I go to, okay, or every day I go to. Let me now try, I will make an sequence, just reducing this one. Look, I'm going to put 0 here. And okay, top P or these different kind of things. I go to, and let me do a completion. Okay, look now, the words that is going to choose is almost every time the highest probability. Look, it will choose the highest probability word every time. Okay, now, if I redo the same thing again, it will do almost exactly the same sentence again, the same thing. Okay, and this is the problem when we have low randomness or low temperature value. Now, if I change this one just a little bit more, okay, and it's not necessarily it's going to give something also meaningful, because highest probability doesn't mean, okay, still it's very low, this one. But now it's generating something different. Let's make something around 0.4. Okay, it started to hallucinate a little bit. And if I put something completely very high, look, it's complete hallucination, doesn't make any sense. Look, it chooses even next words that can be even 0. Look, too much creativity, it means completely not usable. So this means actually we need to, this is a hyperparameter for the inference for the language model to decide about the level of creativity and the randomness of generation. So there is a trade-off to do between low randomness and high randomness. Is this clear? Is it clear for everyone? Is there any question? Okay. So now to summarize and to make the things in a more abstract manner, a large language model, we have as input a context. A context, so this is like a beginning of the sentence. Okay, and the beginning of the sentence here, when you give more context, you will help the large language model to generate more meaningful context. Okay, if you start only by 1 word or 2 words like we did, it's not going to be very effective. But if you give like a relatively good and long sentence, it will be able to predict in a more accurate manner. And here we're going to have an output. So the output, this is a probabilistic text completion. It can differ from one generation to another. It can complete with, I will go to my class, I go to my office in Paris, I go to the school. Okay, this is probabilistic. And this is what the large language model is going to do. It is going to generate text based on a certain context. This is why it's part of the generative AI area. Okay, so this looks pretty much simple. And now we are going to demystify all the logic of a language model, how it's able to understand a certain context and generate a probabilistic text completion that would make sense. Okay, that will be the objective of our lecture. So even making more abstraction, a large language model is nothing but a sequence-to-sequence model. So what does it mean? A sequence-to-sequence model is going to take a sequence as an input, and it will generate another sequence as an output. So the sequence as the input is going to be, for example, text. Text is a sequence because we have a sequence of words. This is the first word, the second word, the third word, fourth, and fifth. And now it's going to generate another sequence, which is also a sequence of other words here. My office in Paris, like 4 words, one by one. So this is what we call sequence-to-sequence modeling. And that means it will require a sequential data in the input. And there are different types of sequential data. It's not only text. So text is the most famous because that's what we use in our everyday life. But it can be also a speech. It can convert, for example, we have speech to text or text to speech. So speech is also a sequential data. We can have time series, for example, stock markets, or trajectory during time, or any kind of time series. It can be, for example, health data, for example, heartbeats or ECG data or anything. It can be DNA. Also, it's considered as sequential data. It can be videos or even images. Now, images by nature, they are not sequential, but we can actually consider them as sequential. There is a famous paper that is called Vision Transformer, which actually consider an image as a sequence of patches. They subdivide an image into a grid. Every element in the grid is going to be a sequence. For example, they made a patch of 16, an image of 16 patches. It will be a sequence of 16 patches numbered from 1 to 16. And this has actually projected transformer to be used also with images. And the video can be also over time. So sequence-to-sequence modeling, they went through the concept of recurrent neural network traditionally. So recurrent neural network was the technology used to process sequence-to-sequence models. And here we have different type of sequence-to-sequence models. It can be one-to-one. For example, one input and one output. So the length of the sequence will be only one, and the output of the sequence will be one as well. We can have also one-to-many. I can provide a sequence with one element, and it will generate a sequence with many elements. I'm going to give you examples of each of these ones. It can be many-to-one. So we have many input and only one output, or many-to-many, and many-to-many, it can be also in different ways. So let's see this in more detail. Okay, so before going even further, I want just to point out about a very interesting paper which dated from 1990. It's called Finding Structure by Jeffrey Ellman in the University of California. And this paper is really seminal. I'm going to provide you some experts from this paper, and you will see that it actually paved the way of what we know nowadays as language models. Okay, this is the first paper that has actually mapped the use of neural network with time series sequences. Okay, so just to highlight you the main contribution of this paper, it has introduced the temporal representation in neural network for the first time. And this actually addresses the challenge of representing the time in neural network models and provide fundamentals for processing sequential human behaviors. The second contribution is the introduction of recurrent neural network. That was the first paper that has introduced the concept of recurrent neural network applied on sequential data. And also, and this is very important, the dynamic memory in the network. So the memory is needed in the context of natural language processing, because when, for example, you have a sentence, the different words inside one sentence, they can have related meaning. So for example, I can refer to a previous word after, for example, 3 or 4 future words in a certain sentence, and we are going to see some examples. So here also this paper has outlined the use of memory in the network and conceptualized the network having a memory for processing sequences. The element into a sequence are not completely independent. They may have some relation, okay, during for a particular sentence, for example, the word in particular sentence, or point into a time series representation. And this is vital for the context understanding in large language models. So, yeah. And these are also some, these are the key concepts. We talked about them. So other concepts also, the internal representation of sequences. Okay, the internal temporal sequence representation, learning and generalization represent the temporal patterns of sequence models, and also has outlined the relevance to natural language processing. So we can consider this paper as the first paper that has triggered what we know nowadays as natural language processing. And these are some examples from this paper. Here, for example, one of the sentences, in short, the network must have a given memory. So this was the first time where we introduced memory into a neural network. This is the concept of what we know nowadays as the recurrent neural network with input units and the context unit. So this is the context, for example, a sentence. And this what could be, for example, the the input of particular neural network, and here the hidden state. So the hidden state, which is calculated from the context and the input, and finally output, which, for example, could be text generation or sentiment analysis, or depending on the task. So it has also represented the time representation of a sequence using one-hot encoding, and also text embedding. And also it has investigated the relation between different words into the text. So this is a very interesting paper, which you can check. It talks about types, tokens, and structural representation of a sequence. Okay, so let's come back to our sequential models. And here are some examples of sequential models. So we already said that we have one-to-one mapping. For example, binary classification. Okay, imagine that, for example, you have an input, the value of coin, and then you say pass or fail, depending on which value you're going to have. Okay, and we can have one-to-many, like, for example, image captioning. Like, for example, if I have an image, so this will be our input. It's only one input, and here I would like to have the captioning. And this is now very famous in language modeling. Okay, and if you have looked at the latest video released by Google, they're going to release Gemini, which is their new language model. It seems to have an impressive capability, and they mentioned that it's going to outperform GPT-4, but still it's not officially released. And it has very high capabilities of not only image captioning, but video captioning. I mean, just show it any video, is going to tell you what's in this video, make you excellent interpretations, of course, using the transformer technology. So the context of many-to-one, we can have, for example, a text, I'm not happy, and we can generate only one output. For example, here, a sentiment. It can be negative or it can be positive. So the machine is able to read a certain sentence, which is a sequence of many tokens or of many words, and will generate only one output, which represent, for example, the sentiment, whether it is positive or negative. So in machine translation, we have the relation of many to many. So for example, I can have a text in English, I love writing novels, and we can translate it in Arabic. And the translation is a little bit more critical because we don't have one-to-one mapping between the words in the input and the words in the output. For example, I can translate this sentence into 3 words in Arabic, or I can translate it into 4 words in Arabic. Okay, so translation, of course, the machine is going to learn based on a large number of samples of data on how to translate effectively the different, the input text into the output language. Okay, any question? Is there any question? Fine. Okay, so now I'm going to take you from the very beginning. I'm going to take you through the history of neural network. Okay, so neural network basically started from the very simple and basic concept of perceptron. It has some inputs that could be data, for example, can be a text or pixel of images, or maybe any kind of features. Okay, x1, x2, x3, usually numbers. And then we have only one node. Okay, a node where we're going to have weights. We're going to learn about these weights, and we will have a linear transformation. For example, what is a linear transformation? It's just multiplying the weights by x1. For example, w1 multiplied by x1 plus w2 multiplied by x2 plus w3 multiplied by x3. And usually we can add a bias. It's not only w multiplied by x, but we add a bias. So it's an additional value. So here we have a linear representation. Okay, so this is what is represented by the sigma. It's a linear representation of the input x, okay, which is the vector x multiplied by the vector w, and we add a certain bias vector. And of course, w1, w2, w3 are going to be learned. In the beginning, we're going to start from random values of w's. And as we input data, we're going to learn the correct value that will provide the correct output. But making just a linear representation of the input, you're not going to learn anything. Nothing is going to be learned because we're going just to project in a linear space. So there is no learning. So what is the learning? The learning comes when we introduce a nonlinear function. So nonlinearity is an important concept for learning, okay, for learning in a neural network. So first of all, we do the linear transformation, which is just wx plus b, and then we will introduce a nonlinear function. It can be sigmoid, it can be softmax, it can be tanh, it can be ReLU. There are so many nonlinear functions, and this basically depends on the type of application. And this is going to generate an output y, which is equal to gz, which is here the output from this function. And finally, we're going to calculate it to the expected value of the output. So now, imagine that this is a sentence, I am happy. And here the output must be, for example, 1, it means positive. So this is going to be a probability. For example, let's assume that I get 0.3 and the objective is to be 1. So we can say that there is a big error between the expected output and the calculated output. So in this case, this error is going to be considered, and we will use back propagation, which just we use here the derivative in order to reduce the error. So you know that when derivative equal to 0, it means we don't have errors. So as the error grows, we're going to here provide the feedback to the neural network using back propagation, and by the calculation of derivatives, and we want that the derivative will be equal to 0, we're going to make adjustment of the weights. So the weight will be adjusted. And this process is going to be repeated multiple times until all the weights will converge to the best model that will reduce the error to the maximum or the loss to the maximum. So basically the error is calculated through a loss function, okay? So the loss is expressed as function of A, which is the output of the nonlinear function, and Y, which is the expected value. And for example, in this very simple case, this is like a logistic regression. It's Y log A plus 1 minus Y log A minus 1. This is one of the possible logistic loss that is used in logistic regression. Of course, it depends on the context. It's not a universal loss function, depends on the objective that you want to minimize. This loss function is going to minimize the error with respect to the expected output when we have an output from the sigmoid, which is a value between 0 and 1. So this is the concept of perceptron. And now one perceptron can be fine if we have a small amount of features, but as we have very complicated features, imagine that you have, for example, an image of 1,000 pixels by 1,000 pixels. We're not going to rely on one perceptron, okay? Because one perceptron is going to have only few number of parameters. And this is not sufficient if we have a large number of, for example, data, and also the data contains a lot of features. So for more complicated scenarios, we're going to just replicate the perceptron. So here we have 4 perceptrons. And every perceptron here, it just has the following structure. It will have a linear function and a nonlinear function. So this is just to learn different type of patterns. The first perceptron is going to learn a particular pattern. The second is going to learn a different pattern, and so on. So we have one layer here. We have the input, and every input is going to be connected to all the perceptrons. And finally, we can have either, so in this case, I have 3 outputs. I can have only one output, depend on the objective of the application. So we're going to start from X that belongs to real numbers. So maybe we have M real numbers as input vector, and they can generate N real numbers at the output vector. So this is what we call the feed-forward neural network. It's just an extension of the perceptron model. Now, imagine that we would like to process sequential data. And I'm going to use the same model here, the feed-forward neural network. I'm going just to represent it as this green box. Now, the sequential data, the difference between normal data and sequential data is sequential data depends on time. I have, for example, one word at time 0, the second word at time 1, and so on, if we consider discrete time. So if we consider this relation right now, this is not sufficient to capture the time dependencies between the different words. And let me explain you how is this. Now, this is now a feed-forward network to capture between xt and yt. But when we say xt, I have the first element at time 0, okay? And the second element, x1, will be at time 1. It will generate y1, and so on. So imagine that I have x0, x1, x2, and x3, and everyone is connected to a feed-forward network. So in this case, when I process this input in this way, there is no relation between this input or this one or x2 or x3. But this doesn't capture the relation between the tokens in a sentence, because there is a relation, basically. When I say every morning I go to the school, okay, every word has a relation between the future word and the previous word. But in this case, they're going to be processed completely independent. So here we have just xt, maybe I'll just change it here. So we have the output, yt is just a function of xt, and it's not a function of xt minus 1 or xt plus 1 or no other token in the sequence. And this is not what we want, actually. We want to consider the relation between the different sentences. So, and this is now the way how a recurrent neural network works. So now, for example, when I calculate the output y0 from x0, and when I want to calculate next the output of x1, I'm going to provide a state, the state from the previous network. So let's call the state h0. So the calculation of y1 will depend from x1, which is, for example, the current word, and the previous word output. So in this case, this word or this token is going to impact the output of y1. And now if I want to do the same thing for x2, I'm going to take h1, which will be a hidden state that will summarize the information coming from the previous two states. And in this case, the calculation of y2 hat will depend on the current state, which is x2. It can be the current token. And this, let me call this as the summary of the previous state, h1, which depends also from x1 and x0, and so on. h2 now will impact the calculation of y3, which will be a function of x3 and the previous hidden state. So this is what makes the concept of recurrent neural network. And in this case, we're going to express yt, or the expected value of the output, as a function not only from xt, but also from the previous hidden state, ht minus 1. And this is what we call actually the memory. So if you remember the paper, the seminal paper that was proposed in 1990 by Altman, it has introduced the concept of the memory, which is very important to process sequential data, because sequential data, every element in the sequence is depending on the previous elements. And we capture the relation with the previous element through what we call the hidden state. Okay, so, and this will make that the output will depend both from the current state which is xt, and the previous state, which represents the memory. And we can basically represent a recurrent neural network either using a sequence similar to this one here in the right side, or it can be something similar to this one. So these two representations are equivalent. Okay, so here we have xt, we have a recurrent cell, and we have a hidden state. So this should be ht minus 1. I have some issues in the notations. Okay, so we have ht minus 1, which is the previous hidden state. And this will impact the output of y. So just to summarize now, okay, we can consider that the hidden state or the current state at a certain point in time will be just a function, okay, based on the weights of xt and the previous hidden state, the old state. So the same functional parameters are used in each time step. So this represents the concept of recurrent neural network representation. Any question? Okay. And this is an example of pseudocode, okay, for the next word prediction intuition. Okay, so if we define a pseudocode for the recurrent neural network, we can consider that we have as input a word, which is the current state, and the hidden state, which is like the summary, okay, of all the previous words. Okay, so the input word is transformed into a suitable format, like for example, when how decoding here, and the hidden state is updated based on the current word and the previous hidden state. So to calculate the hidden state here, the new hidden state is calculated by applying the activation function, can be sigmoid, for example, or relu or tan h, multiplied by the weight w x plus b. Okay, so here we don't have a bias, but with the hidden weight and the previous state plus the bias node. So it's a function of x, h by t minus 1, and the bias. And then to make a prediction, we're going to apply the activation function based on the weights outputs multiplied by the hidden state plus the bias. And we can return both the prediction and the hidden state. So the prediction, this is yt, and the hidden state is going to be the current h, the current hidden state. Okay. So the sequence modeling design criteria depends on, so the RNN have the benefit of processing variable length sequences. So the model should handle varying sequence length. And also it must have long-term dependencies. It means the capabilities to capture distance sequence dependencies. It means when there is a word that has a relation with another word but comes after a certain amount of time, we should be able to calculate the dependency between the different words. And also the direction of information flow. It can be unidirectional or bidirectional. It means we can capture the relationship between a word and the future words, or we can capture the relationship between a word and future word and previous words. Now, depending, for example, if I have a task to fill in the blank. So what does it mean fill in the blank? I have a sequence, I have a sentence, then I have an empty word, then I have another sequence, and I want to find this empty word, what will be the value. So in this case, I would need to have bidirectional flow. I need to analyze the previous sentences, the previous sentence, the future sentence. This will help me to find the word that will come in the middle. Now, if you have text generation, the context will be only the first word in the sequence. And I want to infer what will be the next token. So in this case, I will have a unidirectional flow because my inference will depend only on the previous context. So the direction of the flow in an NLP task will depend on the application itself. Okay, and the order of information. something very important in NLP, we need to maintain the sequence order for accurate interpretation. Okay, for example, if you say every morning I go to the school, you cannot say school, morning, I, every go. So the order of words is really very important. And this is one of the reasons that we need to maintain the sequence order, because it's not just a matter of having the same words, but to have them also in order. Okay, if you lose the order of the words, so you cannot have any good prediction. And the good thing in recurrent neural network and its variants that they naturally maintain the sequence of the words, because these words are processed in sequence. So I know that this word, okay, when I train this neural network, this word comes first, so it's processed first. So naturally, the order of the word is maintained because it will depend on the time when it will be processed, because all the words will be processed one by one. So naturally, they will be processed in order. So we don't have to worry too much about the ordering in recurrent neural network and its variants, but we will have to worry more about them when we talk about transformers later on. So just remember what I'm saying right now, because the order of the word is really very important in any natural language processing task. And also another advantage of RNN is that they are able to handle variable length sequences. And this is something very beneficial. For example, we don't need to specify in advance what is the context length. It can manipulate variable text sizes. For example, AI is breakthrough technology, or I can provide AI stands as a pioneering technology. It will complete by today, or artificial intelligence represents the forefront. So the number of words, it's not an issue when we talk about recurrent neural network, because they are going to process one by one until the end of the sequence. However, in transformer, this is a little bit more tricky, and of course, there will be a solution for this. Now, coming back to the memory and the importance of memory. If we look at the recurrent neural network, of course, the hidden state is going to capture, let's say, a summary of all previous words, but will not take into account of a particular word into that previous sequence, whether a particular word has a particular relation of another word that comes afterwards. So the hidden state is like a digest. It's like a summary, a global summary, of course, grain summary of all the previous context. This could work, but it might lose accuracy when we want to capture the relation between future word with some particular words in the sentence. Let's see this particular sentence now. When we say, despite the cat's initial fear, the dog became its best friend. So the cat initially has fear from the dog, and later on they become friends. So when we say here best friend, so this word here, best friend, it has a relation, it's actually referring to the cat. Using a neural network or recurrent neural network, when I come to, for example, generate the word best or friend, I'm going to have just a hidden state that will summarize all the previous context. But here, I would like to, it doesn't mention any relation between friend and cat. And now this is why the research community, they have proposed to use another variation of recurrent neural network, which is called LSTM, which is the long-term short LSTM, short memory dependency, long-term short memory, to capture the dependency between the different words in the same sentence. Okay, so the idea here is actually to devise a recurrent neural network that is able, okay, when it learns from so many texts, it's able to understand the relation between any two different words in the same sentence. And of course, here we have to specify a memory window. For example, now, if I count the number of words, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I need to have a memory, for example, of 8 words, 10 words, 20 words. Of course, if I increase the memory, that will add more complexity in terms of processing, in terms of memory size, but also it will be able to capture the relation between any two words in within that memory. If the memory is small, for example, if I make a memory of 4, so I will stop here. Okay, initial feel the dog. So there is no word within this context. So it's less likely that I will find relation between different words. So the memory size or the memory length or the context length is another hyperparameter introduced in LSTM networks. So this is a summary between LSTM and recurrent neural network in general. Okay, just I'm going to talk about some technical issues. So either you have questions or we will take just 2 minutes to refresh, and then I'm going to be enter again into the technical details. Do you have any questions? Okay, so let's get back. So as already presented before, so recurrent neural network is efficient in processing sequential data. However, they fail to capture the relation between some distant words. And this is why the LSTM was proposed to enhance the traditional recurrent neural network by incorporating a memory system that will manage both the long and the short-term dependencies, okay, through different techniques, as we are going to explain. So you can see now the internal mechanics of recurrent neural network is just a simpleton H function, nonlinear function that will capture the transformation between the input and the hidden state. And here we have some more complicated design of the architecture. We have different type of gates. So this is what we call a gate. We have a forget gate. We have an input gate. We have a stealth state update gate and the output gate. I'm going to explain this in all details. And that will make that what actually will introduce the memory. So the memory is going to be introduced into this upper arrow here, which we call the conveyor belt. And you can think about it as like a lane that will just carry out information from the previous cell and the current cell after doing some transformation. So the LSTM, it introduces some more complex structure with the concept of gates to regulate the information flow. Okay, introduce different type of gates, as already mentioned, forget or output gate, input gate, for better memory management. And it will be able to select what information to keep and what information to forget. Okay, so it only tries to keep the most important information that to capture the relationship between the different words. And another advantage of LSTM is that it is less prone to the problem of exploding and vanishing gradient descent because of the gated operation. So the output is going to be more regulated. So we don't have risks or high risks as compared to the RNN for vanishing problems or exploding gradient problems. So let's look at this in more detail. Okay, so the first idea in the LSTM is the idea of the conveyor belt, okay, which is this part of the architecture. Okay, so it is a mechanism that will carry out the previous cell state. So the cell state, this is going to be calculated at every cell, okay, and it carries out some important information. This is what we call the memory, okay. The memory is what we carry from the previous cells. Okay, and the gate within the cell will regulate the information flow by considering the past inputs, so the information from the previous input that might be relevant for future prediction. And if we take an example, for example, in language processing, this could be the subject of a sentence, which is needed to understand the verb that comes later on. Because the previous sentence, when we do language modeling, we want to predict the next word. So the cell state here is going to carry out the important information from the previous sentence to increase the probability of generate the next word in a more meaningful manner. And also, it helps to capture the temporal relationship, which tries to understand the dependency or the patterns that will be learned over the time, such as the relation between certain words or a text in, or for example, some different points in time series data. So these are the main points that will be carried out by the conveyor belt or the cell state here. Okay, the previous context, and also capture the relationships between different words or different points in time series data. Okay, so how this is done? Of course, what information we are going to carry about, it will depend from what comes here below. And let's see this in more detail. So basically, the LSTM gate defines 3 types of gates. The forget gate, which decides what is the important information that we need to keep and carry out in the memory, and what is the less important information that we need to discard. Also, the input gate decides which new information to store in the cell, which will be this one. And the output gate decides what part of the cell state is relevant to the output of the current time step. Let's see in this detail. And these are the different, let me stop this one, okay. These are the different equations that capture the LSTM different gates, but let's make the things more simple. So this is the concept of the forget gate. So the forget gate is basically relying on the sigmoid function. So what is the relation between sigmoid and the information to keep or to discard? So let's look at the characteristic of the sigmoid function. It basically generates a value between 0 and 1. So if you provide any input to the sigmoid function, it's going to generate a value between 0 and 1, depending on the value of x. Okay, so what does it mean 0? And what does it mean 1? So if the output of the sigmoid is 0, okay, of course, this is something that it will learn over time. It means that this information is not really very important. It's not really very important. I'm going to discard it. And if the output from the sigmoid is going to be high and closer to the 1, the closest it is, the most important it will be considered. And this is the information that will be considered to remember. Of course, how is going to be forgotten? When the value is close to 0, so the contribution of that information to the output is going to be not significant. Going to completely forget. If you multiply by 0, 1, you're going just to remember something very, very small. Okay, and if you multiply by 1, you're going to take the whole information and use it into the next state. Look, and because later on you will multiply this by the output of the previous cell. So this here you are going to consolidate what information is important from the previous hidden state and the current state, and will be incorporated into the memory. Okay, and so at the end, the forget state decides which information to discard from the cell state using a sigmoid function that the output values between 0, which means forget, and 1, which means retain. And at the end, we're going to have a linear function. So the output from here is going to be just same linear function between hidden state and current state, plus a certain bias, and we multiply by sigmoid to generate the value between 0 and 1, and then we multiply it by the previous cell state. So that's the first part. Is it clear? Okay, so now the second part is about the input gate, which is here. Okay, so coming the previous state, ht-1 and xt, okay, the input gate, the objective of the input gate is to update the cell state with the new information that's relevant for the future task, because it will be added to the memory here. Okay, so here it has two nonlinear functions. It uses the sigmoid function, which is here, to decide the significance of the new information produced, which produces also a value between 0 and 1. So basically, it's going to return something similar to here. It will just to have a weight, okay, of the important information or the information that we need to discard, because this will be multiplied. And then the tanh function, okay, is going to provide us. So this is the linear transformation that will result into the new cell state, okay, C, E, and will be multiplied by the forget gate information. And finally, the output will be added. So this is the calculated current state cell, and then will be complemented with the previous cell state, and this will result into the new produced cell state, which represent the memory, by the way. Okay, so the dependencies are captured between the word are captured with the sigmoid function, and the new cell state is captured by the tanh function. And this is now the equation. Same thing, we're going to have weight multiplied by the hidden state and the current state plus a bias, and then the sigmoid. And the output here will be the tanh with another linear function plus a bias. And both of them will be multiplied together, okay, and then will be added to the previous state. Okay, so of course, as already mentioned, after calculating, so we are going to integrate the decision made by the forget state and the input gate, and this will represent the candidate cell state. Okay, just multiplying this function by CT-1, which is the output of the forget state. This is the output of the input state, will be also multiplied by the candidate cell state, and then will be added together over here. And finally, we're going to calculate the output, which will be the HT. This is what we want to calculate as the output. And here we will decide how much of the current cell state will influence the output and which aspects will carry over the next hidden state. So same thing here, we're going to use sigmoid to consider the important information, and then we will multiply the information coming from the cell state by tanh, and finally we'll calculate the hidden state. So all of these represent the core mechanism of the LSTM output gate. So this is, I'm just talking about the history of NLP. All these techniques were used before 2018, and they were considered as the standard technology for natural language processing, recurrent neural network and LSTM. And this is their internal mechanism. And here are some sample papers, okay? So they were extensively used, the LSTM were extensively used in speech recognition, because speech is a sequential data. This is another paper also is on speech recognition, and which uses basically the same equations that we've talked them about, okay, to convert a speech and understand, maybe convert it to a text or do any kind of processing. Okay, so LSTM, it's pretty much simple. There are already open source implementations. So this is an example of Python implementation. And also there is a C++ implementation in PyTorch, and also in TensorFlow. Okay, you just need to call the LSTM method and put the different hyperparameters, and you can easily train an LSTM network by applying any kind of sequential data. Okay, any question? Now we're going to see the transition to transformer. Are all the concepts clear? Okay, so before going now, let me ask you questions. Do you see any limitations of the LSTM networks? So why LSTM networks are now not being used for creating large language model, and why they were not successful actually to create large language models in the way that we see them today, based on the information that they have presented? Anyone has an idea?
Because of the forgetfulness issue?
No, not really this one, because forget is just to select the important information that you need to keep for the next states.
Mm-hmm.
From computation mechanism now. So sequential models are sequential, right? Basically, we need to process them in sequence. Now, if I say this and you have a very large data, what would be the implication? if you need to process very huge sequential data in sequence, one after the one, what this will induce.
Do you mean
Okay.
high temperature?
Yes.
Sequencing large or huge data, do you mean it will induce high temperature?
No, it will induce high processing time, because you need to spend a long time to train this data, because you need to process it one after the other. You cannot do parallel processing in recurrent neural network. I cannot take, for example, a whole text and process all the words in parallel because of the sequential nature of the network.
I see.
Okay.
Got it.
Yeah. So this is one of the limitations. It's slow in training, and also it's slow in training, because in training I need to provide the tokens one after the other. I cannot put them all at once. So this induces that I cannot do too much about parallelization. I cannot process the training into a parallel manner. Okay. We have also the encoding bottleneck, okay, which is also comes from the sequential nature of the different words or the different tokens. And another issue is the short memory. Now, it's true that LSTM introduces memory, but it's going to be always limited. For example, it will be limited to a certain number of words, maybe 10 words, 20 words. I cannot go very far or very large, because at the end, I don't know what will be the minimum and the maximum context length of the sentences. So all these limitations, actually, they have reduced the capabilities of recurrent neural network and its variant to be very large, let's say, language models or NLP tasks. Okay, so in order to improve this, the question was how to eliminate the need for recurrence. Now, the recurrence is the bottleneck. It will make a bottleneck in the embedding. It will make a bottleneck into the training. We have a short memory. So the idea here, instead of processing these words in sequence, okay, over the time, we try to process them all at once. So we try to have parallel processing. We consider the sequence of words as just a continuous stream, and we try to ensure a longer memory size. And the idea is to consider the whole sequential input as just a single input to the neural network. Okay, so instead of considering, I'm going to take, for example, what will be the longest sentence I'm going to have? For example, let's say 2,000 words. Okay, I'm going to consider now a window of 2,000 words and consider all the words and put them at once into a neural network. So that will be the whole memory. It's the sequence, the input sequence length will be my memory. And then I can do parallelization, because I'm going to process all these words all together into a neural network by putting them into a feature extractor module, and then it will provide the output. So that is actually the architecture that has initiated the idea of transformer. So what is the architecture, remember you? When you see this architecture, which of the architectures that we have seen today is very close to this one? So this architecture, basically, if you forget about it, it's nothing but the feed-forward network. This is my whole input. I'm going to put it all together into a feature extractor module, and then we will provide the output over here. So that's the whole story. So basically, the transformer is just the migration from sequential model back to feed-forward network models. Have you seen this analogy or not? So here, we're not going to have any kind of sequence. I'm going to have all my input. It's a text or any kind of sequential data. And I'm going just to send it to any kind of feed-forward network and finally provide the output. Is that clear? Okay, is this point clear about it? So transformer are nothing but coming back to the concept of feed-forward network, but of course the main difference is how I'm going to extract the features. Because now this is a raw data. I'm not going to process the raw data. Of course, I need to process in the beginning. And then I need to find a new way on how I can transform this data into an output by extracting the features inside the neural network. Because what is the role of the neural network? It's just it has feature extractor and also a classification head to tell you, for example, the prediction or the classification or doing some kind of regression. And in this case, by transforming the sequential input, okay, from time series into one block, so we can process all of this in parallel. Now, but of course, this comes with some other limitations because I need to know in advance the length of the sequence. Okay, what is the length of the sequence that I need to buy? For example, if you choose to train a network with the context of 2,000 words, it cannot accept a longer text of, for example, 3,000 words. You're going to limit yourself. Okay, if you say, okay, let me try to train it for 100,000 words. Of course, the training is going to be more complicated. You will need more memory. You will need more processing capabilities, and it becomes a challenge. So the context window, it depends from several factors. It depends on the scale of your data. It depends the capabilities of your hardware resources to train a model. But at the end, okay, let's assume that we can provide a certain context length, and then we will train it as a full, feed-forward network, similar to this one, which will enable parallelization and long memory management. And this actually was the core idea of the paper, which is released in 6 December 2017. Attention is all you need. And here the authors have applied this concept, and they have proposed a very seminal feature extractor module that is called self-attention. Okay, and from that time, the transformer and the self-attention becomes a standard in processing NLP tasks. And just 1 year later, we have seen the start of what we know nowadays as language models. The language models, they started to be developed from 2019 based on the transformer architecture that we are going to provide all details today. And this is the paper by itself. Now, if you are from the research community, you can see how many citations from this paper. I remember when I did this training back in April and May, the number of citations was 75,000. And just in 4 or 6 months, it added more than 20,000 citations for only this paper. That's a huge number, This paper is making the difference in artificial intelligence completely. And it was proposed in the conference NeuroSIP, which is one of the flagship conferences in artificial intelligence. And this paper basically has applied the idea of self-attention and transformer to the task of machine translation. Okay, and they come up with this architecture. Okay, so this is the architecture that was proposed in this paper, and which was used as machine translation. So just to give you an intuition about what they've done, they provided the original text as input here, and they trained this encoder-decoder transformer architecture by providing also the output translated text. And then the input text will be processed by an encoder, and then the output text will be processed by a decoder, and finally, it will generate it will be trained to generate the translated text at the end. Okay, for our case in language modeling, we usually don't need to have an encoder-decoder architecture. So basically, we only use encoder or decoder architecture. I'm going to explain this in more detail, But now what is important in the next slides is to understand this different module. Okay, so the input embedding, this is something that you have done in the previous lecture with Dr. Al-Hawari. And now we try to understand what is a self-attention module, what is a multi-head attention module, what is normalization, okay, how the feedforward is used, okay, another normalization layer. Also, what is the difference between a decoder and an encoder? This is what I'm going to present into the next slides. Also, the concept of positional encoding, which is introduced here on how to keep the problem of positions, okay, into a neural network. Okay, so first of all, I'm going to start with the concept of attention, which is very important. So look at this picture. Maybe some of you have attended some of my previous lectures and you know what's this about. But now for those who attended this for the first time, do you see anything particular in this picture?
I noticed
so
a
it looks
cheetah.
like a picture. Yeah. So yes, there is a cheetah, maybe because now you are in front of the screen, but usually when I do this in the classroom, it doesn't look easily. Now, when you don't put too much attention, so the coarse grain observation is that we have mountains and we have snows, and that's what actually is pretty much looking. But if you put more attention here, okay, we can identify a pattern that is different from the mountain and from the snow. But this pattern is not really very clear. So usually computer vision algorithms, if they are not trained well, they might fail. And even we as humans, now when I presented these multiple times, almost nobody was able to observe the cheetah, especially when we make it on a projector screen. But when you see this more carefully, you're going to observe that there is a cheetah in the picture. Okay, now same thing in NLP. If I say, you know, this is a word and how you can spell it. Of course, there are many ways. How can I spell this word?
خير حبر.
Yes, خبز. خير مثل ما قلت. So we can spell it in multiple ways. So if I tell you, give me with confidence what is this خبر نعم. If I tell you, give me this confidence, what is this word? You're not able to know. Okay, you can give me, for example, 10 suggestions. But now, for example, if I do the following, اشتريت, I give you this word, وأكلت. So here for sure, you will provide me the response with more confidence. Okay, اشتريت خبزا وأكلت, because now, from the context that you have learned before, you know what will be this word. Because in all your history, when you learned a lot of text, you have read a lot of text, you know that when you have this word between these two words, اشتريت وأكلت, so it's likely to be this one with more confidence. Now, if I provide the following now context, قرأت, this word, جميلا في الجريدة. So this is going to be for sure خبرا, لأن هناك علاقة بين القراءة والخبر والجريدة. كيف عرفت هذا الكلام؟ طبعا لأنك قرأت نصوص كثيرة في السابق، وتعرف أنه هذا إذا جاءت قرأته والجريدة تعرف أنه الكلمة غالبا تكون خبرا. طبعا this is probability, but it's very high probability, especially if you have already a pattern like this. Okay, لكن لو فرضنا ما نخليش مثلا حروف خبر، ممكن تكون قرأت مقالا، قرأت ما أدري أي شيء في الجريدة، لكن لما نضيف الباترن هذا، okay, so you have more confidence that it's going to be this, okay, this word خبرا. So same thing, اشترى الخطاط هنا حبرا، لأنه في علاقة بين الحبر والخطاط والمخطوطات. فالعلاقات ما بين الكلمات، احنا عندنا في ذهننا خريطة تربط العلاقات ما بين الكلمات، خريطة ذهنية للكلمات. فالترانسفورمر واللانجوج موديل كل ما يقوم به هو إنشاء هذه الخريطة. كيف يتم إنشاء هذه الخريطة؟ من خلال إدخال عدد كبير جدا من الكلمات. فإذا مر لي عدد كبير جدا من الكلمات، الطريقة التي أنشئ بها المحولات ولا الترانسفورمرز هي في الأخير خريطة ذهنية لعلاقة الكلمات مع بعض. هذه هي الفكرة. اوكي سو ذا كونتكست مانر لقد قام ب باش تكون جبري خاطر هذا المسكين. جبر. من كان يؤمن بالله واليوم الآخر فليقل خيرا أو ليصمت. فنلاحظ الآن ملاحظة واضحة أن هناك علاقة وثيقة جدا ما بين الكونتكست وما بين الكلمات. ف when we train a language model we're going to guide it to find this type of patterns, this type of relationships by making attention to the words and the relation between words, okay, with each other. Okay, this is the main concept of the idea of transformers, is to find the relationships between words. So at the end, الخريطة الذهنية هذه ولا the relational map will be captured by a probability, okay, or likelihood that a word is related with each other within a certain context. طبعا مثل ما قلنا من قبل, the information flow can be unidirectional or bidirectional. Okay, مثلا in the previous cases I did here, this is kind of bidirectional because if I tell you find this word, you're going to be able to read the previous sentence and the next sentence. This is what we call like filling in the blank, يعني finding the missing word, إيجاد الكلمة الناقصة. فنحتاج أن نعرف السياق السابق واللاحق. في التكست جنريشن الانفورميشن فلو ترتبط فقط بالسياق السابق. ف all the objective is try to find the weights or the probability that capture the relation between words within a particular context. اوكي فاحنا نقوم بتدريب الآلة على اساس انه مثلا اذا عندها مثلا سياق معين اللي هو مجموعة من كلمات تستطيع تقوم بإنشاء كلمات لاحقة أخذ عن الاعتبار السياق. طبعا هذا سيكون من خلال طريقة التعلم والمعرفة اللي قامت بتعلمها خلال التدريب حتى في الأخير تستطيع تنشأ مقال. وهذا الآن لو فرضنا باش تبدأ تنشأ مقال لما تبدأ تكتب يمكن أصعب شيء الكلمة الأولى ثم الكلمة الثانية ثم إذا بدأت كتبت 4-5 كلمات خلاص أصبح السياق بالنسبة لك واضح فتستطيع ما نقولش تتنبأ لكن تستطيع تعرف ايش الكلمات التي تأتي لاحقا. فهو كل ما نريد القيام به it's try to mimic how the human are actually generating text, and this is start by a learning phase of books, by reading a lot of things is going to be to have the skills to generate future words. Okay, so same thing even if I have longer context. So مثلا ممكن في إطار الجملة هذه in this sentence there is a high probability between قرأت وخبرا لأن القراءة والخبر عندهم علاقة كبيرة جدا. قرأت والجريدة مثلا يمكن يكون 50% لأن القراءة يمكن تكون على كتب يمكن تكون على مصادر انترنت أو شيء آخر. في يمكن يكون استعمالها أوسع فالعلاقة يمكن تكون مش وثيقة جدا وهكذا يعني. طبعا العلاقات يمكن تكون word by word ولا تكون على إطار context أوسع من ذلك. Is it clear?
Yes. Dr. Anis, what do we call this kind of data representation? Relation capture?
Yeah, this is the relationship between, yeah.
Okay.
No, in a very abstract manner, this captures the relationship. But of course, in a transformer or self-attention, it's even much more complicated. Like in the whole idea, it's around this.
Yeah, it's very clear.
Yes. Any other question? Okay. Okay, so let me now show you also the intuition around the attention. So the attention is not actually, or self-attention is not something new, but it has also its roots into the context of information retrieval. So imagine now in self-attention mechanism, so imagine that you want to search a specific YouTube video, like in this case. So what you will do in the beginning, you're going first of all to specify a certain query, your search query. Okay, for example, I want to search, I have so many videos on YouTube. Okay, I will call this value, for example. Okay, and you will be searching for a query. So I would like to search the word attention. So here I'm going to call it a query. This is the word query is what we use in the context of information retrieval. When you want to retrieve some information, we use query to mention the request or what we want to find in an information retrieval, and we use the word value to mention the whole context from where we are going to search. Okay, so here in our case, the vast collection of videos on YouTube, this is what we call here the value. And later on, we're going to have the search, we're going to have several videos selected. So these are called the keys. So every video that we find based on the query, we will call them a key. Now, which one is more relevant for the search? Okay, so now I need to see the relation between the query and the key. Okay, so for example, now if I look at this one, the relation between query Q and the key one, I can say here it's called demystifying attention in computer vision with convolutional neural network. So there is a high relation between this key and this query because I have here the word attention. So I will give it a score of 0.8. Now, if I look at the second video, which is the second key, here we have Prince Sultan University experience in boosting research innovation. This is less likely to be relevant for the query. So the score here will be very low, 0.2. So if I took another video, I have key 3, okay, it doesn't seem to match too much the query. So I have a score 0.1. So basically we calculate a similarity between the query and the key. And the similarity will result into finding a score which will tell us, okay, how related the query with the key. Okay, this is the whole analogy with the information retrieval. Okay, so the query, it's the specific text or topic that you are searching about it. Okay, from the space, from the explored space, which is our value here, and you have the search space, which is our value. Okay, so basically we have the search space that is our value. We are going to identify several keys, which are the elements that we will find from the search. And then we will do the matching process. Okay, so the matching process, it try to find how similar, okay, the query to the key. Okay, and then we will find the resulting output will be the most likely, okay, the highest similarity between the key and the query. Okay, so this is the analogy between the information retrieval and the query. And this is the same mechanism that we use explicitly in transformer for calculating the similarity between the word and its context. So the context of the word will be the value, or maybe the whole context. And then for a particular query, okay, we're going to identify which key, for example, what is the most likely keyword that will come for a particular context, okay? And this is how we're going to train the self-attention mechanism. Okay, is the example clear about the information search? Any question? Okay, perfect. So this represents actually the intuition behind the concept of self-attention mechanism, which is used in building transformers. So basically, this is the landscape of the self-attention. We will have a query. For example, the query will be a part of the text in the context of text generation. And we're going to have several proposed words that can come afterwards. And then for each particular word, we're going to try to make an assessment about how likely this word can come after that query. Okay, and this is going to be done through a similarity, which is basically done through a dot product. I'm going to explain this in detail technically. And then we're going to have a map, okay, of the weight between the multiple queries and multiple keys. And then I take the whole context. And this context will be multiplied by the map of the weights. And finally, that will help to extract the relevant information. Okay, so to get started with self-attention, okay, let me remind you about, okay, let's take an example where we have an input text similar to this one. Okay, so he wants to play football with friends. So this is a text. Now, if I want to process this in a neural network, whatever self-attention or recurrent neural network, I cannot process raw text. I need to convert this text into, first of all, token. Okay, let's assume that we have word-based tokenization. And later on, we need to convert this word into numbers, which we call input embedding. I think you have learned this last week with Dr. Hawari, which is creating embedding from words. And here, for example, the embedding, it can be of, depending on the size that you want to do, 512 or 1024, that's a hyperparameter. And now we're going to process all these words all together. So if we process all these words together, we're going to lose an important information, which is the relative position of these words. And this is why in a transformer architecture, it is important to attach the position of each word to its embedding. That's really important. How we do that? We're going to also provide a position encoding. It can be simple, like one-hot encoding, or it can be more complicated, like learnable embedding as well. We can learn the positions from the text. And finally, we are going just to sum the position encoding with the input embedding. And all of this is going to result into a position-aware embedding. This step is very important. This is a pre-processing step before even we start to do self-attention. Because remember that we said we're going to use the whole sequence, process the whole sequence at once. Now, this is different from recurrent neural network. If you remember, I told you that recurrent neural network, it processes the input in sequence. So the sequence of the information is maintained naturally because we have a sequential processing. So every word is going to be processed in its natural ordering. However, when we work with transformers, we're going to process all the word at once. So we are going to lose the information about the position of each word with respect to each other. So if we don't integrate the position encoding, later on, the transformer is not going to have any understanding about the logical positions of each word with respect to another. So it can generate you a sequence that is, for example, completely with a complete different ordering: play, wants, football, friends, he, and so on. Now, if we want to train it to maintain the order of the words in a sentence, we need to add the information about the position. So the position will be encoded, and there are different types of encoding. The simplest one is one-hot encoding. For example, number 1 is going to be all zeros. Number 2 will be 1000, and then 01000, and so on. This is what we call one-hot encoding. Or whatever type of encoding that we'll be doing must have the same size of the input embedding, and then we just make a simple sum. So the position-aware embedding is going to be a combination of the text embedding, the position encoding, and then it will be naturally aware about both the encoding of or the embedding of the text and the position of the word or the token within the text. Okay, so this is really important, is to encode the text information and to encode the position information. That's the first step that we need to do. Okay. So we're going to stop now, and we'll come after 30 minutes to finish the technical detail about self-attention. Any question? Is it clear? Okay, let's continue. So thank you for those who responded to the question. It was pretty much good, or two responses. Okay, so let's continue right now. In the base, and we did. Okay, so you're here. بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so let me remind what we've done about embedding, so word and position. So here in these slides, we have highlighted the importance of capturing both the position encoding or embedding in addition to the word embedding as well. So as you already know, we need to embed, to create word embedding. And this is an important pre-processing step to prepare the raw text data for the transformer architecture or for any neural network architecture by creating the embedding, which are input vectors. And we can create the embedding, okay, based on different type of solutions like OpenAI. It has the embedding, or also we can have from Llama embedding. For different types of embedding can be used. And we also define position encoding, and this what will capture the position of each word in the sentence. And finally, this will result into the position of word embedding. Okay, no problem. You can do the quiz whenever you want. It will be available there, and they send you also the solutions. Okay, so now we are going to talk about the self-attention mechanism itself, which is basically related to the query, key, and value concept that we have introduced in the context of searching a video on YouTube. Because this concept, as already mentioned, it's related to the information retrieval, which is already known before. So the goal here is to identify and attend the most important features in a sequence. In our case, it's a sentence of different words or different tokens. So we have already encoded the text information using word embedding. We have also encoded the position using position encoding. And now we would like to extract the key, the query, and the value. So how to do that? So remember from the previous slide, we have generated what we call position embedding. And these are position-aware embedding. Not only position embedding, they are position-aware embeddings, which merge both the information coming from the word embedding and the position embedding or position encoding both together. And there we are going to create the key, the query, and the value. So the query here, so basically all of them, we will use the position-aware embedding, and we will multiply by a linear layer, and this will provide our output. So first of all, the linear layer will just have some kind of random weights, and we consider this as the query. Then we have the key matrix, which be also the multiplication of the position-aware embedding by a linear layer. And similarly, we do the same for the value. Okay, so the only difference is that here we're going to do the similarity between the query and the value. And finally, multiply the query and the key, and finally we will multiply this by the value. So initially, these are random parameters or random weights, and they are going to be learned, provide more text. They are going to be tuned and learned as we go. So this is how we're going to do, and then we're going to calculate the similarity between the query and the value as well. So how to calculate the similarity? At the end, this is a vector representation, and this one is a vector representation, and you like to calculate the similarity between multidimensional vectors. So this is basically done using the concept that you already know, which is called the dot product. Okay, so the dot product is a concept known in linear algebra that allows to calculate, for example, if I have a vector Q, in our case it's the query, and another multidimensional vector K, and we would like to calculate how similar these two vectors are. So the way that we do usually in linear algebra is to calculate the dot product. Okay, so if the dot product is 0, it means that they are completely different. And if the dot product is 1 or maximum, it means they are identical. Okay, so the dot product is the mathematical tool that is used to calculate the similarity between two multidimensional vectors. And this is the expression of the dot product. For example, you have a vector AB and XY. So basically it will be AX plus BY. This will represent the dot product. This is for 1 by 1 vectors. This is 2 by 1 vector, okay? And this is 2 by 2 vector. This is how we calculate the dot product. Okay, so consider this case, for example, Q and K. So here, clearly we have completely identical vectors. So we are going to measure the vector similarity using the dot product. And the dot product in this case is going to give the maximum value. If we make it in normalized manner, it's going to give 1. If we consider that the dot product is a value between -1 and 1 when the vectors are normalized, in this particular case, the dot product will be the maximum, which is the value of 1. Okay, when they are completely coinciding one on top of each other. For this particular case, where we have the two vectors are orthogonal. Okay, so the dot product here, so the two vectors are completely different, and the dot product here will result in 0. So another extreme situation, if the two vectors are opposite. Okay, and here the dot product will give us a negative value. So if they are completely opposite, it will give us -1. Okay, it's -1. Okay, they are completely opposite. So the dot product is a way to calculate or to measure the vector similarity. And this is how we are going to see the matching between the query and also the key. So if the query and the key are very close to each other, we're going to have a high value of the dot product. So in this case, they are likely to be selected. And if the query and the value are not close to each other, so in this case, it's going to the dot product is going to be close to 0, or if they are completely opposite, it's going to have negative value. Okay, but the problem of the dot product, and this is a common problem in deep learning, actually they can generate, if they are not normalized, they can generate very big values or very small values. They can go to -infinity or +infinity. This is what we call exploding, okay? Vanishing gradient or exploding gradient. Okay, this is why we need normalization. And the self-attention mechanisms uses the softmax normalization in order to compute stable attention function. So one way to do normalization is to use the softmax function. And also another way to do normalization is also, or to reduce the impact of the vanishing or exploding gradients, is to use divide the value by a scaling factor. And this is what has been done in the initial transformer paper. they have divided the dot product by a scaling factor, and it's called the scale dot product. So if you read the paper, transformer is all you need. They don't talk about the dot product natively by itself, but the scale dot product where they divide the value of the dot product by a scaling factor to make sure that this value is not going to explode. It's not going to be very high, either in the positive sense or in the negative sense, in the plus infinity or minus infinity. So the similarity scores, and this is what we call similarity scores, or also attention weights. This is how they are calculated. Okay, the attentions captures the relations between the different words. So we have words in the query, we have words in the key, and this dot product, as we are going to calculate them in matrices, is going to calculate the similarity or the relation or the attention weights between these different words. Okay, so the scaling factor, there are different techniques in the literature on how the scaling factor could be calculated. In the initial paper, transformer is all you need. So the scaling factor was chosen to be the dimension of the key. For example, if you have a key of 64 values, the vector size is 64. So you will divide by the value of 64 by dk, okay, which is the key dimension. Another way also to reduce the scale or to calculate the scale dot product is to also to calculate the cosine similarity. That's another approach. It has been used on other papers. Okay, and here you will have the dot product, and you will divide by the norm of the vectors, norm of vector A and the norm of the vector B. That also produces a normalized version of the dot product, okay, which is another alternative to dividing by the scaling factor dk here. But of course, now all of this also, it's a viable solution. It's not pragmatic from some perspective, especially from in terms of computational efficiency. Now, if we compare the scale dot product, which is dividing by a constant, or the cosine similarity. So this is the scale dot product. It's the dot product divided by the square root, basically, of the dimension of the key. And here we divide by the norm. So look at the calculation here. Here you just divide by a value. And here you need to divide by the square root of the sum of A square and the square root of the sum of the B matrix square. This is very computational expensive. And imagine that you are training a huge neural network, is going to kill the computation resources, both in processing and also in memory, because this will require processing in memory for every attention head in the neural network. Okay, so the dot product attention is computationally more efficient than the cosine similarity, and this is an important aspect that we need to take into account when we design architecture, is the computational efficiency. Because even whatever we do for computational efficiency, we're going to spend maybe a couple of days, couple of months to train a huge large language model with tens or even hundreds or thousands of GPU resources. So the efficiency of computation is pretty much very, very important. Also, the cosine similarity, it requires additional computations in addition to the memory, okay, which slow down processing for large data sets. And the dot product are much simpler to compute, which boost efficiency. Okay, now, for example, you might ask why we need to define by dk. That was just a choice for the initial paper, attention is all you need. And if you see the literature, there has been several types of scaling factors different from this value. And basically they are empirically driven. So what does it mean? Based on initial experiments, maybe the researcher will try to find out which of the scaling factor could probably give better results, and they will use it. It's like a heuristic that will be used to drive the experiments. And now, for example, here, even in the robotics and Internet of Things lab, we started to build our first large language model. It will be a large language model in Arabic language. And inshallah, we are going to release the first versions by next week. And from what we have seen in the literature, we will be the first, maybe the research lab that will release 100% trained large language models only on Arabic language, because now there are other language models that are released for Arabic, but they are not trained only on the Arabic language. For example, there is an Arabic language in the UAE, which is released by, I think, Mohammed bin Zayed University with another company. It's called JACE. JACE is trained on 2/3 of the tokens are English and 1/3 of the tokens are in Arabic. And they claim this is for Arabic language modeling, but it's really not the case, because most of the tokens are not really Arabic. But in our case, it's 100% Arabic tokens, and we got actually very good results for the text completion. We are now at the phase of text completion. We're starting by different type of model sizes, and it's getting very good results for Arabic text completion so far, which is going to be also fine-tuned for other Arabic tasks as well. So now I'm telling you this because when we start to train our large language models, we have feel the necessity to really optimize the computation to the maximum to make the model converge in reasonable amount of time. And okay, now, so let's recapitulate what we have said. So far, we have the query vector, we have the key vector. We're going to do a dot product between the key and the query. And this will result into the scale dot product, which is the dot product divided by the scaling factor. And this will result in what we call the similarity scores and attention weights. So the attention score, they capture the pair weight similarity between the query and the query and the key vectors. And this basically will result in the kind of the heat map, الخريطة الذهنية اللي قلنا عليها من قبل. Of course, if it is trained on a huge amount of data, okay, it will result in this kind of mapping between the different words and the relation between them. But still, you know, even though we are dividing by a scaling factor, we could still have some also issues. Now, if we look, for example, this is what we can get from the scale dot product, okay, to calculate a self-attention probability score matrix. And the matrix displays raw self-attention scores. So what we presented are raw self-attention scores representing in-normalized relevance between the words and in a sequence. So this one, it represents the relation between word and sequences, but it's not normalized. Okay, the scaling factor helps reducing the vanishing and exploding gradients, but it's not normalized. When we say normalized, it means that the attention weights has to sum up to 1. Okay, so we convert them like a probability. And to do that, so even with the scale dot product, training a neural network without normalization, we can have high variance, and this will lead to unstable gradients during the training, and it might crash the training process. Okay, so one way to avoid this also is to add a normalization using a softmax function. And the softmax function usually convert the scores into probabilities whose sum will be equal to 1. And this will provide a more balanced attention across the words. Look now, we can have values greater than 1. They can sum up to different values. And when the network is very deep, okay, the lack of normalization will actually lead to having issues with the training stability later on. Okay, so to overcome this, we're going to use, okay, we've talked about the scale dot product, the need for normalization. We're going to use normalization using a softmax. Okay, so what we are going to do, we're going to consider the attention scores and adding them to the value, and we multiply, and we're going to apply the softmax function here. And this will result, instead of having an output with completely values of any order of magnitude, we're going to convert them using the softmax function into probabilities. And the good thing is that the softmax is going to ensure that the sum of these probabilities will be equal to 1. And this will ensure the stability of the training later on. And this is what we actually call the attention head output. So the attention head, okay, it's a module that will calculate the attention scores, okay, multiplying them by the values. It's a multiplication, okay, multiplying them by the values, okay, and then it will result into the attention head. So this is a self-attention module or self-attention head, and we can think about this one as the attention feature map. It's a feature map that will take the whole context, okay, and will capture the relations between every word in this particular context. And now we come to the first equation in the self-attention module. So the attention applied to the key, query, and the value will be the softmax of the key, query, multiply dot product by the query and dot product by the key, divided by the scaling factor and multiplied by. Okay, this is what this is the expression of the attention module. Yep. Okay. So now let's summarize everything for the self-attention head. First of all, we start by building the positional word embedding that we have seen in the beginning. And finally, we're going to apply linear layers to each of them. So the first two ones, we're going to use dot product to calculate the similarity between the query and the key. We're going to apply scaling factor. We're going to apply softmax function. And all of this together, we're going to make a dot product between the value and the output of the softmax function. So all of this together is called the self-attention head. And finally, this represents the following formula here. Okay. Now, if we look at the pseudocode, it's not very complicated to calculate a self-attention head. Okay, so we can define a function that is called scale.product for attention. It will take a query as a tensor. This is from PyTorch. So a tensor is like a vector, multi-dimensional vector, a key, which is another tensor, and the value, which is another tensor, and we'll generate a tensor. Okay, so the query and the query, key, and the value. So first of all, we are going to calculate the score, which is the dot product. So the score will be the result of the dot product. We're going to use query.bmm. This is batch multiplication, matrix multiplication in PyTorch, which just do the dot product between the key and the value. Okay, between the query and the key, sorry. And then we are going to apply the scale. So the scale here, it's the key dot size, okay, which is the, we calculate the square root. And this will allow us to calculate the scaled score, which will be the score divided by the scale. So we are here right now. And then we apply the softmax function. And the softmax function will be applied to the scaled score, which is also a vector. And finally, we return the softmax, okay, then multiplied by the dot product with the value. So all of this is represented by this function. And then to build an attention head, we can create a class that we call attention head, which inherits from module in PyTorch. And we're going to initialize the constructor, and then we create the query, the key, and the value linear transformations, as you can see here. And then the forward pass will be just calling the scale.product on the query, the key, and the value. So this is a possible implementation of a self-head attention in PyTorch. Any question? Okay, that's fine. Okay, so this is just to remind you about the self-attention landscape. We calculate the similarity, we calculate the normalized weights, we make the dot product with the value, which is the stored information, and finally we get the relevant information. Okay, so we achieved the first milestone in this big architecture, which is calculating the attention module. Okay, and now I think you understand pretty much well what is the softmax of the query multiplied by the dot product divided by the scaling factor and all multiplied by the value. Okay, is this part clear for everyone? So we have demystified the first module in this big architecture, and we are going to continue for the others. Any question? Okay. So now we are going to talk about the second module. Now we have one attention head, but here we have multi-head attention. So it means we are going to duplicate this attention head multiple times, and we are going to see the reason right now. So what is a multi-head attention and why do we need it? So the concept of multi-head attention, as we already discussed, it's basically a scale dot product. Okay, we have query, key, and the value. We are going to make matrix multiplication, which is a dot product here, adding scale. We can add a mask. I'm going to talk about the mask. This is optional. I didn't talk about it right now, but I will talk later. Then we apply the softmax, and then we do another dot product. So basically, the idea of multi-head attention, instead of calculating only one multi-head, we're going to duplicate this multiple times, because we expect that every head is going to capture certain type of relationships. Now, when we say that there are relationships between words, we don't know how many relationships. There could be different type of relations. And this is why we need to duplicate the attention head in a way to capture as many relations as possible. So how many attention head we need to add? This is the hyperparameters. It basically depends on the scale of your data, the scale of your network. It's a hyperparameter that you decide to do in advance, trying to optimize the training process. And of course, if you had more attention head, you're going to spend more time in training your network. And so it must be like done in a careful manner. So the multi-attention head is basically creating multiple attentions that will work in parallel. Okay, they will not work in sequence, they will work in parallel. So for the same query, key, and value, we are going to apply them in parallel manner to different attention heads in a way to maximize the relationships capturing between the different word and sentences. So you can think about the multi-head attention in a transformer. It's like viewing a scene through multiple cameras and each capturing different angles. Imagine that you have cameras, for example, surveillance cameras that are monitoring the same region. Okay, so one camera will be pointing from one angle, another camera will be pointing from another angle. So if you want to have a good understanding about what's happening in the surveilled areas, you're going to go to the first camera, have a first snapshot, the second one will give you another observation, the third one will give you a third observation, because everyone will be close to a particular region. So looking at all the cameras from different angles will give you a better understanding about this. Okay. So this is basically the idea of the multi-head attention concept and how it helps to maximize finding or capturing the relationships between the different words. So for people who are more familiar with convolutional neural network, I found out that there is an analogy between multi-head attention in transformer and also the concept of filters in convolutional neural network. You know that when you do a convolution, we're going to do that convolution over several filters, okay, for the same layer. So having multiple filters in CNN, okay, it helps that each filter will extract a different type of feature from the input by focusing on various spatial patterns or special hierarchies. So the same thing, the multi-head, we use multi-head attention in transformer so that every attention head will be able to, like a filter, will be able to capture a particular type of information or a particular pattern for this information. So each head may focus on a different part of a sentence. For example, one attention module will focus, for example, the relation of, especially when the sentences are very long, it can focus on the patterns in the beginning of a sentence, the other one in the middle of the sentence, the third one maybe at the end of a sentence. There could be some overlap, okay, but duplicating the multi-head attentions, it will increase the likelihood to capture as many relations as possible between the different words in a particular contextual perspective. Okay. Okay, so what is the other advantages of the multi-head attention is, first of all, they allow to do parallel processing of independent computation because every attention head will be working in parallel as compared to the other. So this will maximize the efficiency. And it will also allow to jointly attend the information from different positions, okay, and learn different type of patterns for the same sentence or for the same sequence of information. And it can capture both local and global dependency. This is a very important aspect in many areas in artificial intelligence because there is the concept of local and global features. Like if you remember the image that I have provided you in the beginning of the mountain with the snow and the cheetah. Okay, so when you look at the first glance, you're going to focus more on the global information. Like the global information was clear. You have mountains, we have a landscape, we have snows. But finding the local features, it's sometimes more critical. And this is where we need to have attention. Okay, so to find the cheetah, we need to have some particular type of attention mechanisms that will focus on local dependencies, not just globally as the whole image scale, but is going to take a subscale of the image and try to focus, is there any kind of pattern in this particular position? So same thing for the multi-head attention is going to behave in a similar manner. In a particular sentence, there is the global understanding of the sentence in the whole context width. And also there are kind of local understanding. If I take, for example, a subset of the sentence, for example, 20 words or 100 words or 50 words, what kind of patterns you can find from there? And this is the concept of local and global dependencies or local and global features that we need to identify when we train a neural network or, a self-attention module. Okay, this gives a 3D representation of a self-attention module, okay, or a multi-head attention. So for an input embedding here, we have tokens that are converted into embedding, and we're going to have a first query matrix, a second query matrix, and an nth query matrix. So the same input embedding will be multiplied by, okay, it will be transformed into queries, okay, and here we have the different keys. We are going to multiply this query by these keys, and these queries by these keys, and this query by these keys, all in parallel. And finally, every dot product is going to provide us the attention weight. The attention weight for this first attention head. This is the second attention head. This is the nth attention head. And each one will finally provide a linear combination of contextualized embedding based on the output of each attention head. So in this case, we're going to maximize the learning experience of the different type of information that you can capture from a particular sentence. Okay, so creating a multi-attention head in PyTorch is not difficult. So imagine, provided that we have already created the attention head. So basically, we can define an attribute heads, which will be just an extension of the module list. And here we have a list of attention head for depending on the number of heads that we would like to have. So the constructor will have as attributes or parameters the number of heads, the dimension, the input dimension, the query dimension, and the key dimension. Okay. And we're going to create as many heads as required in the number of heads. And finally, we are going to apply this linear transformation, okay, at the end. And this is the forward pass. We're going to apply a linear torch.cut. We are going to concatenate all the different heads that are available in these attributes over here. And to calculate also the equation of the multi-head attention query key and value will be just the concatenation of head 1, head 2, head 3 until the head number h, okay, depending on the number of heads, where each head is just a single attention module, query, key, and the value. This is the definition of the multi-attention head. Okay, so this is just to summarize. The multi-attention head helps splits attention into independent parallel computations. It helps analyze the sequences from multiple perspectives. As already mentioned to you, it's like you are making surveillance of a scene using multiple cameras from different angles. So here we are going to look at the sentences from or sequences from different perspectives. It defines independent, so it also independently operates multiple heads, each capturing distinct information, and combines head outputs for comprehensive understanding. This is what we do for the combination by concatenation of the different head outputs. And this actually improves the contextual awareness that boosts the NLP task performance. So this is now the representation of the multi-head attention. It's just the concatenation of multiple heads that we have seen before. So this is the first dot product, the second one, the third one, and the fourth one. And we're going to take the output of all and concatenate all together. Is there any question? Okay. So now we achieved the second milestone into this transformer roadmap. Okay, so now I think you understand well these equations, and we have completed the concept of the multi-head attention, and also concept of attention here. Now I'm going to talk about the masked attention. I just take 1 minute and they will come back. Okay. So now I'm going to talk about the masked attention, which is also an option that we can add into the self-attention module. So now imagine that you would like to do text prediction or text completion or text generation. So usually, what does it mean in text generation? We're going to give the initial context. For example, when I did the first example, so the first example I have used in the beginning, it was every morning I go to. So I gave only a part of the sentence. So what do I need to predict the next one? But it's not in an option. I have only the previous context. I don't have any information about the next context. So to do the prediction, I need only to consider the previous context to make predictions. So I would like to prevent, even if I have a whole sentence, I would like to prevent the future words from participating in predicting the next one. And this is why we're going to consider, for example, if I have a whole sentence, I will put a mask to the future words. When for example, I have only 3 words, he wants to. So I want to calculate the next word based only on the first words. And I don't take into account the contribution of the future word. So the future word will be just put as minus infinity. So they don't contribute at all to any of the prediction. Now, for example, here, to predict the word play, I will get only the attention weight of he wants to. And this what I need to predict the word play. If I want to predict the word football, I will consider only this word he wants to play until here. Okay, and then all the words that come after that are not considered into my prediction. So because when we provide the text context, we're going to provide this whole sentence. This is what we provide. As you know, we're going to provide the whole sentence, and then we will do our processing task. So to prevent the self-attention of calculating the attention weight based on the future word, we are going to add a mask such that we are going to multiply the mask by the attention matrix, and we are going to cancel the contribution of all future words in the prediction. This is necessary for the tasks like language modeling, okay, large language models, where each word is predicted based on the preceding or the previous words only, and not the future words. So the future words has to be cancelled. The contribution of the future word has to be cancelled by applying this mask. And this is like the first application is the text generation or text completion to ensure that each input is influenced only by the non-preceding text, which maintain the sequential integrity of the generated content. Okay. So applying a mask is also simple. It's not a big deal. Now, if I consider this plot, now after the scaling and the softmax, we're going to apply a mask. So before doing the dot product between the value and the attention weights, so the attention weight will be multiplied by a mask, which is just a triangle matrix, which will have 1 and minus infinity. Okay, we'll have a diagonal of minus infinity, and everything that comes after the first half will be considered as minus infinity to cancel out the contribution of future words in the calculation of this attention feature map. And this is how it is implemented. So we have the same implementation of the score, of the scale, of the scale score, and then we're going to apply the self-attention. So here, probably I did a mistake. I need to have the mask before. Okay? So the mask is applied just on the scale score, and finally, we're going to apply the softmax function after calculating the score over here. And this is how we can update the attention head by applying the mask over here. Okay, and this is the full implementation. So what we added here is just to add a mask, and the mask is optional. Okay, the mask is optional. We can put it as an optional value here. And in this case, it can be applied depending on the task. So if the task is text generation or text completion, we apply a mask, that's usual. And if, for example, finding a missing word in a particular sentence, in this case, we need to have a bidirectional information flow, and we don't use the mask in the self-attention module. Okay, and this is the forward. We just need to apply the scale dot product, mask dot product with attention. So to summarize, this is the implementation of the self-attention module in PyTorch. Okay, and this is in TensorFlow also. Okay, so basically the same implementation. So in TensorFlow, there is the method call, which is equivalent to the method forward in PyTorch. Okay, so now we are done about everything related to attention. And attention, this is the core functionality for transformers. So everything else, like we're going to talk about feedforward normalization. This is not something, related to transformer by themselves. These are some techniques that we apply in any neural network, whatever it is convolution, whatever it is recurrent neural network, LSTM, because besides the feature extractors, so the attention here is a feature extractor, we need to add some additional module for improving the performance of the training, like, for example, adding normalization, additional type of normalization. So normalization is a core technique that we apply in every layer. And the objective is to minimize the risk to have vanishing gradient and exploding gradient during the training. So one module here, which is classical, is a feed-forward network, which can be added just after the output of the transformer. And the objective here is to add additional nonlinearity to learn additional type of patterns and additional type of features. So let's look at the feed-forward network. We have already presented the concept in the beginning of the lecture. Okay, it will take some feature vector in the beginning, will be applied to different types of activation function, and finally it will provide outputs. So the feed-forward network that was used in the seminal paper, attention is all you need. Okay, it will take the input from the output of the multi-head attention, which will be 512. So that was the original version that was trained. Of course, now the current transformer, they have much larger output of the feature attentions. Like they can go up to 1024 or 2048. And now even in the latest version of GPT-4, we can go up to 128,000 output context length. So in this simple example, they have used 512 output of the multi-head attention, and then they applied this to ReLU activation function, and they increased the dimension of the feed-forward network to 2041. Okay, and finally, and then they reduce it back to 512 by applying here a linear function. So they apply ReLU, and then they apply a linear function to calculate an output. This actually adds complex nonlinearity, okay, because we were going to add 2041 activation functions here, which will capture more complex features and will also increase the dimension of the network. And then we're not going to continue working with this dimension. It will be reduced back to the original dimension of the input. Okay. So this is actually the feed-forward network that will be applied at the output of the transformer. So the objective here, so first of all, we increase dimensionality, we apply nonlinearity, and finally we reduce back the dimensionality to the original one. And this is a simple implementation of the feed-forward network. So we're going to create just a simple sequential layer, okay, which has a linear layer. Then we apply ReLU. Okay, so this represents the linear layer plus ReLU activation function. And finally, we're going to apply another linear layer, and that will be the output. Okay. And also there is the normalization layer to reduce the exploding gradient descent. And finally, this is the forward pass. Just apply normalization on the sequential model over here. Apply to X. Okay, just to wrap up right now, we're going to start from positional word embedding. It will be applied to a multi-head attention module. And finally, the output of the multi-head attention will go through a feed-forward network. Okay, so we are at this step right now into a transformer block in the transformer architecture. So this is called a transformer block. Okay, this is the basic transformer block, which contains a multi-head attention and a feed-forward network. Now, this can be trainable. Okay, we can say that this is now a trainable block. We can add as many blocks as we want. But the problem, by practice, if you train this kind of network, you still have likelihood that you can have exploding gradient or vanishing gradient. You know, this is the most dangerous part in the computation when you have exploding gradient. So this is why the researchers, they always try to normalize at each layer. They try to add different type of normalization, especially the problem will have higher risk when the network goes deeper and deeper. Okay, and so another way, another module that was added is the normalization. Okay, batch normalization of the output from both the multi-head attention and the feed-forward network. Now, instead of going directly to the feed-forward network like we have in this basic example, the output of the multi-head attention is going to be also normalized, and the output of the and then the normalized vector is going to be the input of the feed-forward network, and also the output of the feed-forward network need to be normalized again before going into the next transformer block. So the typical normalization in this case is what we call residual connection or residual network. So residual connection network is not something new. It was proposed in 2015 in a famous paper called Network in Networks. And it has been used at that time to minimize the risk of vanishing gradient and exploding gradient and convolution neural network. And it's a concept that is being systematically used in any kind of neural network architecture to reduce the likelihood of vanishing gradient and exploding gradient. And basically what's the idea is to take the input and do a skip connection. So the output from the feed network is going to be merged with the input of the feed network, okay, to reduce the probability that there's going to be a vanishing gradient or exploding gradient. So for example, if I have vanishing gradient here, these values that I'm going to take into the skip connection from the normalization is going to recover some of the lost information in the vanishing gradient that could probably be obtained here. Okay, so this is now we completed the feed-forward network, and now we are going to consider the normalization through residual connection and residual network. Is it clear? Any questions so far? Okay. I hope that there is no problem in understanding. Please, if you want any information, interact with me now. I put you some time just to ask me any question if you have. You can write it or you can speak it. Okay, so the residual connection or normalization, as I already mentioned, it's a concept that was proposed in 2015, and the paper Network and Network is called also ResNet. And so the idea here, look, if you have an output from previous layer, so for example, let's call it X. So doing a skip connection, now we have a weight layer and another. It can be self-attention, it can be fully connected, any kind of neural network architecture here. Okay, so to avoid having any problem of vanishing gradient, so we do a skip connection. This is called skip connection. It means copying the input after the output of maybe 1 layer, 2 layers. Sometimes it can be applied to the output of 3 layers. Okay, it's all these are hyperparameters. And the input here, the output here will be just the sum of fx, which is the application of these 2 layers, plus the original value of x. This is called a residual connection or skip connection, which is used to avoid the problem of vanishing gradient and exploding gradient. Because as you go deep into the layers, okay, you might have any of these 2 problems, okay, which is vanishing gradient or exploding gradient. And this technique has been proven to reduce this effectively and contribute to very stable training of the neural network, especially when it goes very deep. Okay, so this is a simple implementation of a residual network. So we have here a sublayer, okay, and we have a normalization layer, text dimension, and we have also a dropout. So the forward pass will be, we have a sublayer which will be applied to the tensors coming from the top. So we have the tensor X here, and we can apply dropout. Dropout is not shown in this particular picture. And finally, this is the most important part, is that the residual will be the tensor X plus the dropout output, which is, for example, the output from these two different layers. And finally, we apply normalization at the end to normalize the output. That's how it works. And the normalization here, there are many techniques for normalization. And one of them is called the subtract the mean and dividing by the variance. Okay, so here we want to normalize the values such that the mean becomes 0. And this is why we are going to subtract from the expected value or from the average value among all the xk. So the mean here is calculated at every iteration. It's an empirical average. Okay, and it's calculated as the training goes. And this will ensure that at the end, if we replace x hat, x by x hat, so this value is going to be more stable because it will constitute that the average will be 0 and the variance is equal to 1. Let me show you why this is really important. Imagine that you have a distribution of data like this, x1 and x2. So this is not normalized data. So when processing raw data like this, usually you will likely have gradient problems. I mean, what does it mean, gradient problems? Either the derivative will go very high or will go very, very low value. And this will make the network unstable. You can have segmentation faults. You can have out of bounds values and so on. So in order to reduce this risk without even losing the features of the raw data, we can normalize. So now, if I want to normalize the mean around 0, so we can actually subtract the mean, okay, x minus the mean value, and we will have, instead of having all the values just scattered in the space, they will be around the value of 0. So if I make the mean of all these values, they're going to be around 0 here, and this will make them more stable. That's the first problem, okay? Having the value around 0, it will make them more stable later on in the training. But I have another issue. Look at the dispersion of the data points. They have high variance. High variance is one of the other problems and challenges that we face when training neural network in general, because usually with high variance, we will have unstable training experience for the same reasons. So we're going to put the, after subtracting the mean, we're going to divide by the standard deviation. Okay, and dividing by the standard deviation, which is calculated as such, this is the known formula of the standard deviation that we calculate based on the x values. We're going to frame all the data within -1 and 1 standard deviation and within a 0 mean variance. And in this case, we don't lose the feature of the data, but from computational perspective, this is going to lead to a much better experience. Okay, not having any issues later on in deep neural network training. Okay, and here we can see the difference between unnormalized data and normalized data, because the gradient, usually we want that the gradient converge to the central point here, okay, directly. And when you normalize the data, you're going to have a much more regular pattern for the trained data that will help the convergence to much easier to the optimal points. Okay, so there are different types of normalization techniques. We have the z-score, and the z-score, it's basically what we have done so far. We're going to subtract from the mean and divide by the standard deviation. And this is the way how we calculate the mean. It's the sum of all the values divided by n, and n it's the number of values. That's how we calculate the mean. And the standard deviation is just the sum of x minus the mean square divided by 1 and minus 1. So it's pretty much simple. We can calculate this at every iteration in order to normalize the output of the vectors. So another way to normalize also to use the mean max formula. And here we're going to subtract the minimum value, not the average value, and divide by the max minus the mean. That is also another technique used for normalization. There is also the unit vector, where we are going to normalize with respect to the norm of the vector. Okay, that also lead to values, stable values between 0 and 1. So which technique to use? This is also like a hyperparameter. The z-score is very common, but also other techniques like mean, max, and unit vector, they can be chosen by design. Okay. So this concept of normalization is used in what we call the batch normalization. So what does it mean, batch normalization? You know that when we train a neural network in general, whatever it is, a transformer, convolution, recurrent neural network, we're going to train the data batch by batch. So imagine that you have a large amount of data. You cannot train, for example, millions of data all at once. You are going to have saturation in your memory and your processing power. And also the other extreme is that you train the data one by one. And in this case, also, it's not going to be beneficial, first in terms of convergence, and second, in terms of speed. It's like if you train the data sequentially, you will not make any parallel processing benefits. So the thing is the trade-off, depending on the available resources, we can consider data as batches. For example, I have 1,000, the data size is 1,000, for example, elements. I'm going to take 8 by 8. I will take eight data elements, train them, then the next 8 ones, then the next 8 ones. This is what we call batch. So what we are actually going to do normalization is batch normalization. Every batch, we are going to calculate the estimated mean and the estimated variance for that batch of information. Of course, if I change the batch, if I change the data, the expected mean and the expected variance is going to change. Okay, and okay, this is good in the training, but at the end, this normalization that was used in the training, it has to be used also in the inference. If you don't use the same parameter of expected mean and the expected variance in the inference is not going to give you correct information. So the problem here, since we are training several batches, at the end, we try to estimate an average mean and an average variance for among all the different batches. And this will be an empirical value that will be used later on for the inference. And this empirical value heavily depends on the type of data that was used to train the neural network. Okay, so the objective here is to find the most likely data of the variance and of the expected mean among all the different batches that were trained. So later on, we can use in the inference to optimize the output of the neural network during the inference time. And of course, when you train on a large amount of data, you will have a very good convergence from probability perspective. But it might have implications later on. For example, if you are going to use data not from your domain of training, these values can be, reducing the quality of the inference. If the data that we're going to use for the inference is different from the context for which we have trained on. But if we train a large amount of data, usually these kind of discrepancies are going to be smaller and reduced impact. Okay, just to summarize, this is the residual layer. So we can define it as a class. And it's defined by sublayer, normalization layer, and the dropout. And finally, we apply first the residual layer, and then the dropout if we have any. And finally, we apply the normalization. Okay, to adjust the activation using the average and the variance to enhance the training stability, as already mentioned. Okay, that's good. So now we have covered most of the topics. We also covered residual and layer normalization, and yeah, which is this part here and this part. Yeah. Any question? So are you able to follow, or are the concepts difficult? Just want to have a feedback. Can you write me about what you have learned so far? Okay, sounds good. You are following. Okay, so we have covered most of the elements of a transformer block. Now I'm going to come back to the concept of positional encoding, which is used to capture the positions of the tokens or of the word inside a sequential sentence. So let me remind you about this plot. We're going to start from raw text data. We're going to convert it into embedding. And then this embedding will be added to a positional encoding. And finally, we will have a position-aware embedding. Now the question, how do we do the positional encoding? That's what I try to answer in the next slides. So as we already mentioned, there is a need for positional encoding because the self-attention is permutation invariant operation. What does it mean, permutation invariant operation? I mean, imagine that you don't use a position embedding or a position encoding. In this case, when you enter your words, whatever you enter them in any order, the self-attention module is going to behave into the same way. Okay, if you enter the order of words completely different, it's, it doesn't make any sense for the self-attention module. It's just going to try to find the relation between the different words. And this will be a problem later on for the inference because we don't want to have generation into a completely unordered sequence. So this is why we use the positional encoding in order to make sure of capturing the correct order of the sequence in a sentence. Okay, and the self-attention is permutation invariant because it considers all input tokens simultaneously and assigns the weight to each token based on its importance, regardless of its position. So the self-attention doesn't inherently capture the order of input tokens, and this is why we need to add to the transformer addresses this using position encoding, which has structured information, which are the vectors here, to map each embedding vector to each encoding. So there are two different ways on how we can add the position information into the word embedding. The first one is called the positional embedding, or the positional encoding. And we have also the positional embedding. So the difference is simple. When we say encoding, it means we have fixed function. It's not learnable. I mean, it's a static type of embedding. Like, for example, one-hot encoding, its encoding is not embedding because it's a fixed function. It's a static position that we give in advance. However, the position can still be learned. And in this case, we talk about position embedding. So by training a large amount of text, so the position embedding will be able to create embedding vectors that will capture the relation between the different words, okay, in a learnable manner. Of course, both of the techniques are used in modern transformer architecture, but they have differences, okay, in terms of benefit and challenges. So here we're going to train a positional embedding. We're going to add a vector to the input embedding, and all will be trained together. Okay, and this one is actually task specific, because when it is trained, it will be pretty much affected by the type of data or the type of text that was used for training it. Okay, so the parameters here of the position embedding are learnable. They are not very flexible because they will be learned just from the context that is used. So this will lack a little bit of generalization. And the parameter efficiency is low, okay, because of the context-specific learnable parameters. And also it is prone for overfitting. Overfitting because the positional embedding can be will be too much impacted by the type of data. Imagine now that you train a position embedding for text, for example, public newspapers or public articles. And then maybe you're going to try to make inference on different type of information, like, for example, scientific articles or medical articles or any type of different context. So if the position embedding is not trained on this type other in the other and is not trained on other domains, in this case, it might struggle later on to provide you good performance for the inference on other textual domains. However, the position encoding is a fixed function. It's not learnable, so it is task agnostic. It doesn't depend on any particular context. Okay, just a way to capture the relation between the different words, provided that the text, the sequence text is known. So it doesn't have learnable parameters. It's highly flexible, more efficient, and it's not prone to overfitting because it was not trainable. Okay, so the first paper, transformer is all you need. They have used a particular, which is a little bit strange, sinusoidal position encoding, and this is its this is the formula or the equation. So the position encoding, it depends on the position and also on the dimension. And then given the position of the word and the dimension of the vector, they are able to calculate the sine and the cosine values, okay, of the position divided by 10,000 square multiplied by the dimension and divided by the embedding size. It's quite complicated formula here. And it will give a pattern similar to this one, okay? For example, if you have an embedding vector that has 512 elements, okay? So every element will have a position vector. Look now, if we look here horizontally, vertically, this is a position vector for the first word. And then this is the position vector for the second word. And this is the position vector of the third word until you come to the position vector of the last word. And you can see these colors represent different type of numbers. And these numbers are between -1 and 1. Okay, and it gives this kind of pattern. Okay, when you look at the global metrics that relate the dimension to the sequence length, which is like kind of a wavelength. Okay, so these are vectors between -1 and 1, which will be added to the embedding vectors as already introduced over here. Okay, so we will have a vector between -1 and 1 here, and will be added to the embedding vector. And because of this sinusoidal, will give different values. So in this case, the transformer or the self-attention head will be able to distinguish the position of the vectors within a particular sentence. Okay, so the positional encoding, it has some advantages and drawbacks. So the advantage is that emphasis on relative position, because this is a cyclic pattern in the sinusoidal encoding, could highlight the importance of relative position in a sequence. Okay, and it has also ability to extend to longer sequences because it is cyclic. Here the length is 512, but it can be easily extended to, for example, 1024 or 1048, because it has a cyclic pattern. So it should not be an issue here. And one of the challenges, maybe it could be also a challenge or a benefit. It's non-learnable encoding. So being non-learnable, it means that it is completely independent from the text, but also the advantage is not going to be subject to overfitting. So this has a dual position, whether it is a constraint or a pros or a cons. Okay, we can see it in different ways. And the potential inaccuracy for extended sequences, especially, for example, if I use the same position encoding for 0 or 513, that would be also confusing. That will be confusing to distinguish whether this is 0 or 513. Okay, so this is an implementation of the position encoding in PyTorch. Okay, this is the function here. It will take a sequence length, the dimension of the model. Okay, this dimension. And okay, device, this is whether we use CPU or GPU. And first of all, so the position will be torch range here, sequence length. It will take the whole range between 0 and 512, both for the position and for the dimension of the vector. And finally, it's going to apply the cosine and the sine of the phase. So it will calculate the phase, which is this formula, no formula that we have here. We calculate this, we call it the phase. And finally, it will be applied to the sine and the cosine alternatively, whether it is an even position or an odd position in the sequence. Okay, so we have covered everything right now: the position encoding, different transformer layers, feed-forward network, and so on. Okay, any question? واضحة الآن بالنسبة لكم الماب هذه أو لا؟ واضحة الرود ماب؟ Okay, good. So we take 5 minutes breaks and we continue the transformer architecture now from encoder and decoder perspective, inshallah. So now we have completed the description of all the different components of the transformer blocks. Okay, so this is a transformer block right now. But now to create, for example, a large language model or a transformer machine that will process an input text, it can take different type of architectures. Like, for example, this one is called an encoder-decoder architecture for machine translation. And also we have other type of architecture for language modeling and so on. Okay, so just to let you know that the transformer architecture consists of an encoder and a decoder, and each composed for multiple layers. So encoder-decoder is not something new. Autoencoder architectures are already known from 2015, 16, and so on, have been pretty much used in natural language processing, also in certain types of computer vision applications, like image segmentation, for example. And usually the encoder, it will start from raw information or let's say the input data, and then will represent a feature representation of the data. It will encode the data into a feature representation, like a vector, for example, feature vector or so on. This is what we call encoding. And the decoder will do the opposite thing. It will take a feature representation and will decode it to generate the data that we can later on use. Okay, this is the difference between encoder and decoder in general. And for example, just to give you an understanding about this architecture that was used in machine translation. So the paper, attention, is all you need. It consider an input of English text here and would like to translate it to German. And then they used an encoder to create a feature vector from the transformer modules here of the English text. And they used the feature vector from the English text here with also the feature vector representation of the German text to later on process it into the decoder, and generate the German translation of the English input text. So the decoder will decode the feature. Look now, it will decode the feature of the English text and try to reproduce the original, sorry, it will take the features of the English text and also the features of the German text to generate the translated text based on like the input. It will learn how to generate the original text like the input here. Okay, and like for example, the input, the English, and the output will be German. This is the objective, or this is the role of the decoder. Okay, so the architecture has already self-attention module, multi-head attention, feed-forward, positional encoding, embedding, word embedding, and layer normalization. We have talked about all these different components in the previous slides. So the encoder processes the input sequence and converts it to a feature vector, and the decoder, it will generate the output sequence based on the features vectors. That's the idea. Okay, so GPT, for example, ChatGPT, it's based on an encoder-only architecture. Okay, and this architecture consists only of an encoder layer to process the input sequence. So it starts from a text and position embedding, and then it will apply the self-attention module 12 times. Okay, this is the original version of ChatGPT. And finally, it will provide a text prediction and the text classification. Okay, based on the input here. And so ChatGPT is one of the language models that was developed as an encoder-only architecture. There are some other language models that are developed as decoder-only architecture. Let me show you a website that we have done a couple of months ago, which shows you several language models and all this their information. I will share with you this website if you are interested to learn about it. And you can find, for example, GPT-3, if you want to know, for example, let's say GPT, everything related to GPT. And here it says, okay, it's decoder-only architecture, or this variants of GPT. You can, for example, check for llama models. Okay, decoder-only architecture. You can, for example, check, give me the encoder-only architecture, for example. Okay, you can find different. And now when you click on any model, you will find its category, it's the model size, how many billion parameters, who released the model, and all the different type of resources, the abstract, if there is any paper, and so on. That is a repository that we put here like an open source. You can also add, you can create an account and add a new language model through that interface. Of course, you need to be signed in, and add your information. Okay, and here also the category, what is it is pre-trained or fine-tuned, and so on. Okay, you can play with this one. Let me come back. So GPT-based models are unidirectional self-attention. And I think now you know what's this about. It means that they used a masked attention here, masked multi-head attention module. So this is normal because the objective of the language modeling is to predict the next word based on the initial concept. You're welcome. Okay, so the objective of the language modeling or text generation is to predict the next word based on the previous context. So in this case, we need to use a mask when we develop the self-attention module. And this is why we use masked attention. So the use of self-attention, like complete transformers, these models use self-attention to detect and understand dependencies in the input data and capture the dependencies within the input data. So this is the original model of the GPT variations, which has contributed to the release of ChatGPT. So now, how do we create an encoder layer? So far, what I have shown you as a code, it actually denotes one self-attention or one transformer block. But basically, building a complete transformer architecture, you will need to replicate the block multiple times. For example, here it was replicated 12 times. It can be replicated 100 times, depending on how deep you want to define your network. And this is why we need now to take all these blocks and define a particular architecture by repeating them either as encoders or as decoders. I'm going to show you the implementation details. Okay, now considering this model here, we have text and position embedding, then we have one attention block that contains multi-head, masked multi-head attention, their normalization, feedforward, and their normalization, then the text prediction here. Okay, so the transformer encoder layer, it defines one layer of the transformer encoder, and it has the following parameters: the dimension of the model, and this is actually the embedding size. Okay, the embedding of each token, how many elements in each embedding, input and output, tensor size. So the number of heads, how many times you are going to repeat the self-attention head here. It can be 8, can be even more. We have the dimension of the feedforward network, which is this one, 512, like we have seen in the previous slide, and also the dropout. Dropout is a kind of regularization technique that is used to reduce the overfitting problem. And it consists of canceling some of the neurons during the training to reduce the dependency of the output on the data that is being used for the training. Okay, so these are the different parameters. Okay, dimension of the model 512, which is the embedding size, the number of heads 6, for example. We're going to create 6 attention module in the multi-head attention. And the feedforward network 2048. If you remember the feedforward network, we start from 512. We increase the scale to 2048, and then we decrease the size to 512 again. Okay, this is the role of the feedforward network. So this is the constructor here, and then we can define the. So these are the parameters. We initialize the super constructor. We define the dimension of Q, the dimension of the query, and the key, which is equal to the dimension of the model, 512, divided by the number of heads. When we do, and this is an important thing, probably it was not mentioned in when we talked about multi-head attention. So when we create a multi-head attention, every attention module is going to take a part of the sentence. Okay, so the dimension of the model will be just divided by the number of heads. So every attention module is going to focus on a particular perspective of the text. Okay, so it will be distributed on the attention head. The dimension of the model will be distributed on the attention head here. And then we create the attention module, which is we apply the residual layer, then on the multi-head attention layer, which takes the number of heads, dimension of the model, dimension of the query, and the dimension of the key. And finally, we apply the dropout as well. Okay. And we define the feedforward network also. It takes a residual skip connection and then apply it to the feedforward network. And it applies dropout for regularization. And the forward here will be just applying the self-attention module because this is self-attention loop. So the key, query, and value will be all of them the source text itself. Okay, this is called self-attention because we start by the key, query, and the value. All of them, they are equal to the position-aware embedding, which is applied to this module. Okay, so that represents one transformer encoding layer. It's only one layer here. All of this is one layer for the encoder. Now, transformer encoder with multiple encoder layers. Okay, so now we define the transformer encoder. This layer is going to be repeated 12 times. Now we are reproducing the same implementation of the initial paper. Transformer is all you need. Okay, these type of numbers, you can change them depending on your context, depending on the size of your data. These are hyperparameters. But now considering this one, we're going to define a transformer encoder, which will be just, okay, 12 times the transformer encoder layer that we have defined before. So of course, we define the number of layers, the dimension of the model, the embedding size, the number of heads, feed forward and drop out. And then we define the layers here of the transformer encoder will be just the number of layers, which is 6 in our case, can be 12. Like in this example, we're going to have a list of transformer encoder layer with all these different parameters. So basically, we are going to use this class to create a list of transformer encoder layers, okay, depending on the number of heads that we will be considering, okay, in the constructor. And the forward pass is going to take a tensor, which is the source embedding vector from here, okay, and then we're going to, for every layer, we will apply a layer at the source, okay, from here. So this will be the function that will transform the embedding into the output. And finally, we will output the transformed embedding vector at the end over here. Okay, so the transformer encoder is built from many transformer encoder layers, as already mentioned. And the output, so the last layer output, the tensor, output tensor is returned to the encoder output. Okay, so this is about the encoder, and you can do the same thing for the decoder. Just give me a minute. Okay, so the decoder layer now, as implemented in the initial paper. So here we're going to have a few differences. So this decoder layer, it takes a masked multi-head attention, okay? And later on, it will take also an input from the encoder layer, which will comes from the encoder layer, which is about the feature representation of the English text. Because don't forget that now this is the implementation of the machine translation using a transformer. That is the first paper that is called Transformer is All You Need. Okay, and this is how it is implemented, the transformer decoder layer, only one layer of this transformer. We're going to take also the dimension of the model, 512, the embedding size, the number of heads, it's 6. And the dimension of feed forward is this one the same, and the dropout value is 0.1. So, okay, now, same thing, we're going to define the dimension of the key and the query, okay, which is the dimension model divided by the number of heads. And we define the first attention module, which is this one. Okay, it's a masked multi-head attention. And look now, this is the multi-head attention here for the first one, and the second multi-head attention for the second one. This is just definition, and we have a feed-forward network. Now look at the forward pass. The forward pass here, the first attention module, which is this one, is going to take the target text, okay, from the output embedding, and is going to do self-attention on the German text that comes here, which will be the output of the translation. So at the end is going to create a feature map for the English for the German text until here. So that will be the output here, and so on. And now, if we look at the second attention, okay, it will take the memory. So it will take the information coming from the encoder. What we call memory here is the information coming from the encoder. So we have the query is the German text, and we have the key is the English text, and we have the value is the English text. The value will be the German text, yes. German text is the query, and the key will be from the English text. So this is what we call cross-attention. It's not self-attention. Why we call it cross-attention? It's because we're going to have an attention attending the two different source of information, one of them from the English text and the other one from the German text. So this is why we call it cross-attention. Self-attention, it means from the same context, and the cross-attention is from two different contexts. Since here we have a machine translation, so the second attention module is going to be impacted by the text coming from the English version, or the English version feature vector, and the German version feature vector. Both of them, we're going to study the relation between the translated text, and finally, we will generate the translation based on the output of the second self-attention module. And finally, we apply the feed-forward network. Okay, so the transformer decoder layer, this is one, and we will do the same thing for a transformer decoder. We're going to apply this multiple times. Okay, so now to create a whole transformer, and so our transformer here, it contains an encoder layer and a decoder layer. Okay, and so first of all, we define an encoder. Okay, so the encoder, it contains all these different type of information that we created in the previous classes. And it has the number of layers, dimensional model, number of heads, dimension of feed forward and dropout. And the decoder here, same thing, it will have the same parameters, which we define them in the constructor. And finally, we're going to apply the decoder, okay, into the target and the encoder of the original text, which is the source. So this is the source text, this is the target text, and we're going to decode this combination to provide the final translation of the source text. So don't worry about this, because inshallah, the next lecture, we are going to go into details of all these different type of blocks. We will build them from scratch, and finally, we will use a particular text to train a transformer, and you can see the output for text completion and generation. So the objective is just to get familiar. I know that there are so many information, will be heavy information, but don't worry about this, inshallah. The next lecture will be purely practical, purely implementation, and we'll go from the basic concepts, dot product, and so on, until we come to the implementation of the full transformer architecture. And inshallah, we'll be running a very small training for initializing text completion, like a pre-trained transformer for text completion. Okay, so this will be now the implementation of transformer module. But of course, now when you want to use transformer, you don't need to do that from scratch. There are so many open source implementations, even in TensorFlow or in PyTorch. You can use them out of the box. They are optimized, but now from learning perspective, it's really good to understand how a transformer is built from scratch. So later on, even if you use these implementations, you will have all skills and knowledge to even change them and understand their internal mechanics, which is really very important to be an advanced stage when to work with pre-trained language models. Okay, is that clear? Okay, that's fine. So I'm going to finish my presentation with just providing some typical applications of transformers. Of course, transformers are being used in several applications like sentiment analysis. And of course, one issue of transformers is basically related to the data. Okay, so when you have small amount of data, the use of transformer is not really recommended. because the convergence is very complicated. And transformer is not the solution for everything. For example, in several applications like time series prediction and analytics, the use of transformer was not found more efficient than classical LSTM and recurrent neural networks. And that could probably because of the amount of data used in this kind of application is not huge enough to guarantee the convergence of transformer to a good statistical significance. This is not only the case for this. Also, for example, transformer was used in computer vision applications, like the vision transformer. You can see the vision transformer paper. And it's only Google that were able to do a pre-trained vision transformer because they have used billions of images of data that only Google has them. The data set is not even public, okay? And they made all this to show that transformer can outperform convolutional network. But when you do training a convolutional network with classical data and compare against the transformer, most of the time, training a transformer on a small amount of data will not lead to good result at all, not even competing with existing techniques like convolutional network in computer vision or recurrent neural network and LSTM in NLP tasks. So always training transformer will require a huge amount of data, really huge. And this is why it usually requires huge computing resources, but not everyone can afford them to get pre-trained transformer accomplished. Okay, so it can be used for sentiment analysis, for machine translation, also for creating conversational models, for fine-tuning text summarization. Also, it's an important application. All these applications now are out of the box in ChatGPT and sophisticated language modeling. Okay, it can be used also for time series prediction. So the good thing in transformers, when they learn from a huge amount of data, they are able to achieve not only holistic knowledge, but they are able to achieve particular skills that other types of neural network. But other types of neural network are not able to. I don't know, but are you hearing me? Okay, so this is the summary of the application, as already mentioned: sentiment analysis, text generation, the use of text for text summarization, language translation, and mass language modeling. So this is a paper for attention is all you need. I would like just to make you a summary of this seminal paper, okay, and how they have trained their transformer for machine translation. So this paper, it used the WMT 2004 English-German datasets with around 4.5 million sentence pairs for training. Okay, so now these slides are going to show you the amount of data. And imagine this is like the first transformer. I mean, one of the smallest transformers that are being trained, because now we talk about billion parameters of the transformer. And this require, look at how many sentence pairs, 4.5 million. This is the size of the data set. So it means there are 4.5 million sentences in English and their translation in German to be able to train this transformer and demonstrate that it can it outperform classical machine translation based on recurrent neural network and LSTM. So the encoding here, they have used byte pair encoding, which is called BPE. It was introduced last week from Dr. Hawari and was used for sentences, resulting in a shared vocabulary of 37,000 tokens. This is for tokenization. And additional data set for English, French, they used larger data set with 36 million sentences and 32 word piece vocabulary size for the token. Okay, so for the training, the hardware training was performed on a machine equipped with 8 NVDA P100 GPUs. Okay, so you can see now the scale of the resources that was needed. And P100 was like the A100 that we have now at back in 2017. That was the most sophisticated GPU at that time. But I think now the whole training can be done on only a single A100 or probably two A100 GPUs. So the base model, we specified hyperparameters. The training step was around, one training step took 0.4 seconds, and the training lasted for 10,000 steps. It means 12 hours. So they spent 12 hours to train a machine translation from English to German using their 4.5 million pairwise sentences. And for big models, took 1 second per step. For the other model that is bigger with more data from English to French. And when we're trained on 300,000 steps, which took 3.5 days. Look, when you increase the scale of data for the same transformer, okay, or for a bigger transformer, everything will be exponentially increasing from 12 hours to 3.5 days, and 100 steps is not sufficient to converge. You need even longer number of steps. So when you increase the scale, it's a big problem, because not only your data is going to scale up, your size is going to scale up. You will need to train for more epochs, and this will increase dramatically the time you need to have a converging model. Okay, so these are the results here. And from machine translation performance, the transformer model achieved recorded blue score of 28.4. So the blue score and the root score are typical metrics that are used to measure the performance of NLP tasks, but in some cases they give only a very broad understanding of the performance, because usually the real performance is when a human is going to evaluate the type of translation. But from this type of classical metrics, they found that the big transformer, it achieves the highest blue score, which means that this is the best performance as compared to all previous models they compared with byte-nate convolutional approaches or LSTM approaches and so on. And the transformer here have shown dramatic improvement as compared to other models. And from this time, the transformer has attracted an unprecedented attention from all the community, and they started to build over it, not only for machine translation like in this case, but for language modeling, which now has resulted to ChatGPT and related models. Okay, so now this table summarizes the differences between recurrent neural network and transformer. Transformer doesn't come without disadvantages. Okay, so the advantage, for example, if we look at the advantage of recurrent neural network, they are able to process input sequences of any length. Okay, but the problem of transformer, it can only process sequences of a fixed length. This is why we have a fixed context length for the transformer. It's excellent for sequential data and temporal dynamics. It's less computationally intensive for shorter sequences, not like, for example, the transformer, and the parameters are shared across all time steps, reducing the total number of parameters. Now, the pros of the transformer, they can handle long-range dependencies better than RNN, because RNN, although they can have memory with LSTM, but the memory will be very small as compared to the context length that we can have in a transformer. And this helps to manage better long-range dependencies between the different words. And it avoids vanishing gradient problems through different types of normalization techniques that we have covered in the previous slides. It has the ability of parallel execution and processing during the training. Hence, it's faster, theoretically faster, but of course, there are other problems like the quadratic complexity of the attention module. It makes it also very hard to process the information fast or the data fast. And the self-attention mechanism provide context for any position using the position encoding. But the limitation now, let's start by the limitation of recurrent neural network. There is a difficulty in capturing the long-term dependencies based on due to the vanishing gradient. So the problem of vanishing gradient here is more critical and this prevents RNN and its variant to have long-term dependencies. We cannot go very deep into the network because of this issue. Okay, and requires more computation. So sequential computation makes parallelization hard, as already mentioned, and susceptible to issues with exploding gradient in addition to vanishing gradient. For the transformer, the limitations are it requires more computational resources, especially with the quadratic complexity of the self-attention module. It doesn't inherently model the temporal sequential information. This is why we include position embedding, okay, so that we make the model aware about the ordering of the word or the token in the sequence. And the third limitation, the position encoding required for sequence data. Okay, of course, this to solve the problem. And the computational grows quadratically as well. As I already mentioned, it has a quadratic complexity for the self-attention module. Okay, so summarizing, high computational cost, the limitation of transformer, extensive memory for attention matrices, and this is why we use GPUs like A100 with 80 gigabyte of RAM inside the GPU to be able to handle all these attention matrices. And because of this memory consumption, sometimes you cannot even increase the batch size more to a certain limit. If you increase the batch size due to a certain limit, even big GPUs like A100 are not able to handle the whole batch for processing during the training. Okay, and also limited interpretability. And this is one of the issues related to explainable AI, is that these language models, these large language models, they work perfectly and they have excellent skills, but still the research community is not able to understand and interpret why this is happening. And from which point in time, when the scale grows, these large language models will have these kind of abilities and skills to solve very complex problems. Okay, the complex inner workings and decision processes within a transformer are very hard to understand. And now there is a big trend about explainable AI that are trying to explain how AI is actually working. So in order we can control more the different type of outputs and the different complexity that it manages its internal mechanics. But the transformer, it makes it really hard, because when we increase in the data scale and in the scale of the network start to have impressive capabilities that are hard to interpret. Okay, so also the inefficient online learning, because usually when you pre-train a transformer, it will only be based on the information that it has been trained on. And if you remember in the early days when ChatGPT was released, it says I am limited to September 2021. So if you ask anything later after September 2021, it's not able to respond. But now this problem has been solved to a very good extent by considering not only the information within the pre-trained transformer, but also we can access to information through different type of agents. And we have covered this into the LangChain, into the LangChain lecture, where we can connect when we can collect a large language model, for example, to the internet or to a database or to a PDF file. So we're not going to rely on the knowledge of the pre-trained transformer, but we are going to bring the knowledge from other sources of data. And this is what we call retrieval augmented generation. For example, if I connect to a database, or if I connect to a CSV file or a PDF file, getting the information from there, then I will take this context, put it into the prompt, and the language, I'm going to use the language model not as a knowledge source, but as a skill source or a reasoning engine. So from the prompt and the contextual data, the LLM will be able to reason about the question, understand the contextual data, and provide you valuable response. So this actually overcome the inefficiency of the online learning, because now we don't need to retrain the language model every time I need to have new information, but I can use a particular language model connected to either other data sources, and finally I can augment the knowledge of the LLM from other data sources and use the LLM to reason about the data and provide valuable outputs. And some of the papers that were released in 20 May 2023, okay, they tried to reinventing RNN by considering transformers. I didn't see much echo since that time. That was an emerging paper in May, but that shows that there is a trend to combine the benefits and advantages of RNN with the benefits and advantages of transformer. And I think if this is going to happen, we can have new types of language model that will take benefit of both technologies to improve the different type of tasks for language models and text generation. Okay, thank you very much. I come to the end of my presentation today. And if you have any questions or any information, please let me know. Is it fine? Okay, I will try to send you some questions that will help you to go back to the slides and try to consolidate your understanding. I will send you multiple choice questions, probably through a platform that I have developed. So after you respond to the question, you can get the feedback, an automatic feedback of your responses, what is correct, what is not correct, and how to improve, inshallah. Thank you very much for your attendance, and see you next week, inshallah, for the closing lecture about building a transformer from scratch and developing a pre-trained language model. Thank you. Assalamu alaikum wa rahmatullah.